Space is not normal. It is not quiet, predictable, or familiar. The deeper we look, the stranger it becomes. The universe is filled with objects that break our expectations, events that twist the laws of physics, and mysteries that do not fit into the simple picture we learn in school. When we talk about strange things in space, we are not talking about small curiosities. We're talking about discoveries that challenge everything we thought we understood about reality. And the strangest part is that we keep finding more. The universe is not built for comfort. It is built with extremes. Objects behave in ways that feel impossible until we understand the forces behind them. Stars flicker in unnatural patterns. Planets float without suns. Entire galaxies fade and reappear. Light bends around invisible objects. Energy comes from sources we cannot see, and signals reach us with no clear explanation. These discoveries do not just surprise us, they push science forward. Begin with the simple idea that space should be predictable. Stars should shine steadily. Planets should orbit suns. Gravity should act in ways we can measure. But the moment we look deeper, that picture breaks. Space is filled with things that do not follow the usual rules. Some of these discoveries happen by accident. Some happen through careful observation. But all of them force scientists to rethink what the universe is capable of. One of the strangest discoveries we made is that most of the universe is missing. When astronomers measured the motion of galaxies, they found something shocking. Galaxies rotate far too fast for the amount of visible matter they contain. According to normal gravity, galaxies should tear themselves apart. The stars should fly outward like sparks, but they don't. They stay together. Something invisible is holding them in place. That invisible something is what we call dark matter. Dark matter does not shine. It does not absorb light. It does not interact with normal matter except through gravity. We cannot see it, touch it, or detect it directly. Yet it makes up most of the mass in the universe. This means the universe is mostly made of something we cannot observe. We know it exists only because galaxies behave as if something heavy is pulling on them. That alone changes our understanding of space. The universe is not what it looks like. It is built on invisible structure. Then we discovered something even stranger: dark energy. Instead of slowing down, the expansion of the universe is speeding up. Gravity should pull things together, but the universe is spreading apart faster over time. Something is pushing everything outward. That something is dark energy. We don't know what it is. We don't know where it comes from. But it makes up most of the universe. The fact that space is accelerating is one of the strangest discoveries in modern science. It tells us that space is not empty. It has energy built into it. Now think about the space between galaxies. It looks empty, but it contains strange objects we never expected. We discovered enormous radio circles, massive rings of radio energy with no clear origin. These ORCs are so large that they span hundreds of thousands of light years. They appear suddenly and surround entire galaxies with faint halos. We don't know what causes them. They might be shock waves from massive events. They might be remnants of ancient explosions. They might be something else entirely. Space is filled with these unexplained phenomena. They appear, fade, shift, and sometimes repeat. They break patterns. They challenge theories. They force us to reconsider how energy moves across large distances. And they remind us that we have barely started to understand the universe. Another strange discovery we made is the existence of rogue planets. These are planets that do not orbit any star. They drift through the darkness, completely alone. Some are the size of Earth, others are as large as Jupiter. They wander freely, pulled only by the gravity of the galaxy. How they form remains a mystery. Some may have been ejected from their star systems. Some may have formed on their own in deep space. These planets are cold, silent, and almost impossible to detect. Yet there may be billions of them in our galaxy alone. Then we found stars that behave strangely. One example is Tabby's star. Its light dims and brightens in irregular patterns. No natural explanation fully fits. Dust clouds, shattered comets, and energy fluctuations have all been proposed. But the pattern remains unusual. It is one of the most mysterious stars ever recorded. Watching it is like watching a cosmic light switch that refuses to follow any rule. We also discovered pulsars, spinning neutron stars that flash beams of energy like cosmic lighthouses. They are some of the densest objects in the universe, formed when massive stars collapse. A sugar cube-sized piece of neutron star would weigh as much as a mountain on Earth. These stars rotate incredibly fast, some hundreds of times per second. Their pulses are so regular that they act like natural cosmic clocks, but not all pulsars behave predictably. Some slow down suddenly, some change their energy output, some switch off and on. Their behaviour is strange and still not fully understood. Then there is the wow signal, a burst of radio energy detected in 1977. It lasted only a moment, but it was so unusual that scientists marked it with the word wow in the data. It came from a region of space with no known stars or planets. Nobody has ever detected anything like it again. It remains one of the strangest signals ever recorded. It might have been natural, it might have been artificial, or it might have been something we have no category for yet. Space is also filled with objects that stretch our imagination. Consider quasars, which shine brighter than entire galaxies. They are powered by supermassive black holes, feeding at extreme rates. The energy they release is staggering. Then there are magnetar, neutron stars with magnetic fields so powerful they can wipe data on a hard drive from across thousands of kilometers. Even a safe distance feels dangerous in the presence of a magnetar's magnetic field. Another strange discovery is fast radio bursts, or FRBs. These are intense millisecond-long bursts of radio energy that come from all directions of the sky. Most FRBs flash once and never repeat. A few repeat in irregular patterns. Their origin is unknown. They could be collapsing stars, neutron star collisions, magnetars, or something we have not yet imagined. Their intensity is so high that some bursts release more energy in a single instant than the sun emits in days. Then we discovered entire stars made of metals, white dwarfs that crystallize into diamonds the size of planets, supernovae that shine brighter than galaxies, and black holes that collide and send ripples through space-time. Every discovery pushes the boundary of what we consider normal, but some of the strangest discoveries are not objects, they are behaviours. Light bends around invisible things. Galaxies rotate faster at their edges. Some galaxies have almost no dark matter. Others have almost nothing but dark matter. Some galaxies are larger than they should be. Others are too small. Some appear suddenly. Some fade into darkness before they should. These are not small details. These are signs that the universe behaves in ways we still do not fully understand. Even the shape of the universe itself is a mystery. We do not know if it is infinite or finite. We do not know if it loops back on itself. We do not know if it has edges or boundaries. Some observations suggest it is flatter than expected. Others hint that it curves slightly, like the surface of a sphere. This uncertainty is part of what makes space so strange. The more we look, the more questions appear. Why do some stars flicker as if something is passing in front of them? Why do some planets exist where they should not? Why do distant galaxies show patterns that seem impossible? Why does reality behave differently at cosmic scales? These are not trivial questions. They shape our understanding of the universe. Every strange discovery adds a new piece to the puzzle. Some pieces fit, some do not. Some require new theories. Some demand new physics. The universe does not reveal its secrets easily. But this is the beginning of the journey. The strangest things in space are not just curiosities. They are paths to deeper understanding. Each discovery forces us to rethink our assumptions. Each mystery pushes science forward. Each unanswered question starts a new chapter in our search for truth. In the next parts, we will explore these discoveries one by one, the strangest objects, the strangest signals, the strangest behaviours, and the strangest ideas that space has forced us to confront. The universe is not just large, it is unpredictable, and the deeper we look, the stranger it becomes. 2. The stars that break the rules. The universe is filled with stars, but most of them behave exactly as we expect. They shine, burn fuel, grow old, and eventually die. Their lives follow predictable stages, but not all stars fit the pattern. Some stars flicker in ways that break logic. Some shine with impossible brightness. Some collapse into dense structures that behave like nothing else in nature. And some send signals across the universe that challenge our understanding of physics. These stars remind us that space is not consistent. It contains objects that push reality into unusual shapes. Begin with the stars that flicker strangely. The most famous example is Tabby's star. At first glance, it looks normal. It is a little larger and hotter than the Sun. It sits far across the Milky Way, but its brightness changes in ways that defy explanation. Most stars dim in regular patterns when planets cross in front of them. Tabby's star dims unpredictably. It drops in brightness by as much as 20% for no clear reason. Sometimes the dimming lasts days. Sometimes it lasts weeks. Sometimes it returns to normal. Sometimes it doesn't. No planet could cause dimming this large. No dust cloud could behave so irregularly. Scientists proposed ideas ranging from shattered comets to unusual dust grains to giant ring systems. None of them fully explain the pattern. Tabby's star remains one of the strangest stars ever observed. Its behaviour suggests that space contains processes we still do not understand. It is not evidence of something artificial, it is evidence of something unfamiliar. Then there are stars that pulse with extreme regularity. These are pulsars, neutron stars left behind after supernova explosions. A pulsar rotates incredibly fast, sometimes hundreds of times per second. It sends out beams of radiation from its magnetic poles. As it rotates, these beams sweep across space like cosmic lighthouses. Each pulse is precise. Each rotation is predictable. Some pulsars are more accurate than atomic clocks. These stars teach us about extreme density and magnetic fields. They show us that matter can compress into states far beyond anything on Earth. But even pulsars have strange behaviours. Some suddenly slow down, glitching as if their rotation stumbled. Others switch between different energy states without warning. Some pulsars disappear for days, then reappear as if nothing happened. These inconsistencies challenge our understanding of neutron star interiors. Something inside these stars shifts, cracks, or rearranges under unimaginable pressure. Then there are magnetars, neutron stars with magnetic fields so powerful they distort atoms. A magnetar's magnetic field can break molecular bonds across long distances. If one passed near Earth, it would erase electronic data instantly. Magnetars can release sudden bursts of energy that outshine everything nearby. They produce flares that can alter radiation levels in deep space. Their existence shows that the universe contains forces far stronger than anything we can replicate. Some magnetars emit bursts of energy that resemble fast radio bursts, creating confusion about the true origin of those mysterious signals. A magnetar flare in 2020 produced a burst nearly identical to a fast radio burst, but much weaker because it was nearby. This suggests that at least some FRBs might come from magnetars, but others are too powerful and too distant for that explanation. This mix of possibilities shows how stars can mimic phenomena we once thought unrelated. Now think about variable stars that shift brightness slowly over decades or centuries. These stars swell and contract in long cycles. Their behaviour teaches us about the balance between radiation pressure and gravity, but some variables behave erratically. They brighten too quickly or dim too slowly. Some appear to have swallowed planets. Others eject massive shells of gas that drift into space like cosmic smoke rings. One example is the star VY Canis Majoris, one of the largest known stars. It is unstable, shedding huge amounts of material into space. Its eruptions are chaotic. The shape of the clouds surrounding it is irregular and difficult to explain. This star shows how massive stars can behave unpredictably as they approach the end of their lives. Another extreme example is Eta Carinae, a massive system that erupted in the 1800s without becoming a supernova. It expelled more energy than a typical supernova event, yet the star survived. This supernova imposter burst created giant lobes of gas, forming a strange hourglass shape. Eta Carinae may erupt again, or it may collapse directly into a black hole. Its unpredictability makes it one of the most mysterious stars in our galaxy. Then there are stars that orbit black holes. These stars experience intense gravitational effects. Their light shifts in unusual ways. Their motion reveals the mass of the objects they orbit. The S stars near the centre of the Milky Way move at incredible speeds. They whip around the supermassive black hole with velocities that reach thousands of kilometers per second. Their motion is so extreme that it confirms relativity in ways few other observations can. Some stars behave strangely, even when far from black holes. Hypervelocity stars travel at speeds that can eject them from the galaxy entirely. These stars are flung out by gravitational interactions, often after a star in a binary system is consumed by a black hole or exploding companion. They race through space at millions of kilometers per hour. Their existence shows that the galaxy is not a quiet place. It throws stars away like debris. Then we discovered stars made almost entirely of metals, stars with unusual chemical signatures, and stars that appear older than the universe itself. One star, HD 140283, also known as the Methuselah star, initially appeared older than the calculated age of the universe. After revisions, it remains one of the oldest stars known. Its age challenges our understanding of early cosmic formation. It suggests that star formation may have begun sooner than expected, or that our measurements of cosmic time need refinement. Another strange type of star is the white dwarf that crystallizes. As white dwarfs cool, their interiors form carbon and oxygen crystals. Some white dwarfs essentially become giant diamonds floating in space. These stars exist silently and fade over billions of years. They represent one of the strangest endpoints of stellar evolution, a star that becomes a frozen crystal sphere. Then consider supernovae that defy explanation. Some supernovae shine brighter than entire galaxies. These hypernovae release unimaginable energy. Some supernova explosions do not leave behind neutron stars or black holes. Others explode twice. These events are rare and strange. They challenge our theories of how stars die. Even stranger are the stars that refuse to follow their expected lifespans. Some stars live far longer than models predict. Others collapse before reaching their predicted end. Some grow larger than theoretical limits allow. These exceptions suggest that our understanding of stellar physics is not complete. Internal mixing, rotation, magnetic fields, and binary interactions all complicate star evolution. Stars can pull mass from companions. They can merge quietly. They can split apart. Each new discovery reveals another layer of complexity. Then there are stars that disappear entirely. In 2019, astronomers observed a massive star in a distant galaxy vanish without a supernova. The star simply stopped shining. The most likely explanation is that it collapsed directly into a black hole. If that is true, then not all massive stars end with an explosion. Some slip quietly out of existence. This discovery changes how we think about star formation, death, and black hole creation. Some stars behave like cosmic engines. They emit jets of plasma that stretch across light years. These jets interact with surrounding gas, creating shock waves and complex structures. These stars often exist in binary systems where matter flows from one star to another. The transfer of matter creates intense energy. These systems teach us how gravity and magnetism combine to produce extreme behavior. Then we discovered stars that orbit each other in ways that defy expectations. Some binary stars share atmospheres. Some transfer matter. Some merge. Some spiral inward and explode. Some create gravitational waves that we can detect on Earth. These binary systems are laboratories for extreme physics. They show us how interactions between stars create new, unexpected outcomes. Now think about the stars located at the edges of galaxies. Their motion reveals the presence of dark matter. They move too fast to be held by visible mass alone. These observations not only led to the discovery of dark matter, but also revealed that the structure of galaxies depends on invisible forces. The stars behave strangely because the universe contains more than we can see. Stars that move unusually, stars that flicker irregularly, stars that collapse unexpectedly. All of these discoveries show that the universe is not built on simple rules. Stars do not always behave predictably. They stretch the boundaries of theory. They produce unexpected energy. They challenge the foundations of physics. But the strangest stars are not just those that behave oddly. They are the ones that break our expectations entirely. They hint at processes that do not fit our models. They reveal gaps in our understanding of magnetism, gravity, nuclear reactions, and cosmic structure. These stars show us that the universe is not just a collection of lights. It is a dynamic system filled with evolving, unpredictable objects. Some stars follow rules. Others write their own rules. Every unusual star we discover expands the limits of what we think is possible. In the next part, we move beyond stars and explore the planets, especially the ones that behave so strangely that they look like science fiction instead of reality. Some planets rain glass sideways. Some are dark as charcoal. Some reflect almost all sunlight. Some orbit two suns. Some float alone in space. These discoveries will reveal just how bizarre planetary systems can be when seen across the galaxy. 3. The planets that shouldn't exist planets were once expected to be normal. For most of human history, we assumed that other planets would look something like the ones in our solar system. Rocky worlds near their stars, gas giants farther out, stable orbits, predictable temperatures. But the moment we started discovering exoplanets, that picture collapsed. Planets behave far more strangely than we imagined. Some orbit too close to their stars, some orbit far too far. Some have no stars at all. Some have atmospheres that break logic. Some are so extreme that they seem more like science fiction than science. One of the first strange discoveries we made was the existence of hot Jupiters. These are gas giants the size of Jupiter but orbit extremely close to their stars. Some orbit in just a few days. Their temperatures can reach thousands of degrees. They are so close that their atmospheres are constantly blasted by stellar radiation. No one expected giant planets to form so close to stars. According to traditional models, gas giants should only form far from heat, but hot Jupiters exist everywhere. Their existence forced us to rethink how planets move after they form. Many may have formed far out and slowly migrated inward, pushed by the gravity of gas and dust. Then we discovered planets that orbit two suns. These circumbinary planets move around both stars simultaneously. Their skies would show two stars rising and setting at different times. Their temperatures change dramatically depending on where both stars are in their orbit. Movies imagined worlds like this, but reality shows that these systems exist in large numbers. Some planets even remain stable despite the chaos of two stars pulling on them. Now consider the planets that orbit so close to their stars that they are essentially boiling. One example is a planet where the temperature reaches over 3,000 degrees Celsius. At these temperatures, rocks vaporize, metal melts, the atmosphere glows like a furnace. Some of these planets are so hot that they have glowing day sides and dark night sides with enormous winds, carrying vaporized rock from one side to the other. These planets break every model of how atmospheres behave. Then there are planets that rain glass. On one such planet, microscopic glass particles blow sideways at thousands of kilometers per hour. This world is deep blue from scattered light, but the beauty hides extreme violence. Winds flow around the planet so fast that they carry fragments of silicate that act like glass shards. Any spacecraft entering such an atmosphere would be shredded instantly. Another strange world reflects almost no light at all. It is darker than charcoal. This planet absorbs almost all radiation from its star. Its surface is black. Its atmosphere may contain exotic chemicals or molten clouds that swallow light. Space contains planets that look like voids, nearly invisible except for the faint outline of starlight. But some planets are the opposite. They are so reflective that they shine like mirrors. One such world reflects more than 60% of the light that hits it, making it one of the brightest planets ever discovered. Scientists still debate what makes it so reflective. It could have clouds of crystallized particles. It could have metallic vapors forming a bright shell. Whatever the cause, these planets show how differently atmospheres can evolve. Then we discovered planets with the density of styrofoam. These worlds are large but extremely light. Their atmospheres are puffed up clouds of hydrogen and helium. They are so light that if you could place one in a giant ocean, it might float. These low-density planets defy expectations. How can a planet be so large and yet so thin? Heat, radiation, and unusual formation histories may play roles, but the exact processes remain unclear. At the opposite extreme are planets more massive than anything in our solar system. Some have masses dozens of times greater than Jupiter. These objects blur the line between planets and brown dwarfs. Their gravity is so strong that they may compress themselves into unusual shapes. Their interiors reach temperatures and pressures far beyond anything on Earth. Now think about planets that orbit stars in almost impossible ways. Some orbit backward, moving in the opposite direction of their star's rotation. This suggests violent past interactions, collisions, gravitational scattering, or close encounters with other planets. These retrograde orbits reveal that planetary systems can be chaotic, unstable, and reshaped long after they form. Some planets orbit so fast that a single year lasts only a few hours. These worlds hug their stars at distances smaller than the diameter of our solar system's inner planets. Their temperatures are extreme, their atmospheres evaporate, their surfaces may be molten seas of rock. These planets should not survive, yet they do. Then we discovered rogue planets, worlds wandering alone through space without stars. They drift in the darkness, pulled only by gravity from the galaxy itself. Some may have been ejected from their home systems. Some may have formed alone in deep space. These planets are cold and nearly invisible, but there may be billions of them. More rogue planets than stars. These worlds represent a hidden population in the galaxy, silent and lonely. We also found planets that orbit dead stars. When a star becomes a white dwarf, red giant, or neutron star, it often destroys nearby planets. But some planets survive, others migrate inward after the star dies. Still others form from material left behind. One such planet orbits a pulsar and likely formed from a debris after the supernova explosion that created the neutron star. This planet should not exist, yet it does. Some planets orbit stars that barely emit heat. Brown dwarfs, objects between stars and planets, produce faint light. Yet they host worlds that receive almost no radiation. These planets may be some of the coldest in the universe. Their atmospheres could contain exotic molecules not present on other worlds. Now consider planets with unusual shapes. Some planets are stretched into ellipses because they orbit so close to their stars that tidal forces distort them. They are not spherical. They are elongated, pulled by the intense gravity of their suns. These shapes show how powerful tidal forces can be when distances shrink. Then we discovered planets with strange compositions. Some may be made mostly of carbon instead of oxygen and silicon. These carbon-rich planets could contain layers of graphite and diamond. Their surfaces might be shimmering sheets of crystallized carbon. Their interiors might be solid diamond structures. These diamond planets show how different planets can be depending on their environment. Some planets have atmospheres filled with exotic chemicals, methane oceans, titanium vapor clouds, sulfur storms. Space is full of such phenomena. One planet's atmosphere contains metal vapors that condense into metallic rain. Another's atmosphere contains vaporized sodium. These compositions reveal how diverse planetary chemistry can become under extreme conditions. Then there are the lava planets. These worlds orbit extremely close to their stars. Their day sides are seas of molten rock. Their surfaces glow with heat. Their night sides are slightly cooler, allowing lava to freeze temporarily before melting again as the planet rotates. These planets are in constant motion, reshaping themselves. With each rotation, one of the strangest discoveries is planets locked in tidal equilibrium. Their day sides always face their stars, just like the moon always faces Earth. The day side is scorched, the night side is frozen. Between the two lies a thin region of twilight, a ring where temperatures might be stable enough for unusual atmospheres or exotic weather patterns. These worlds show how rotation and gravity interact to create new environmental possibilities. We also found planets with exaggerated seasonal cycles. Some orbit in highly elliptical paths, bringing them close to their stars and then flinging them far away again. Their temperatures change dramatically. Their atmospheres expand, contract, freeze and evaporate depending on where they are in their orbit. These planets experience seasons more extreme than anything on Earth. Some planets are so close to their stars that they are slowly evaporating. Their atmospheres stream behind them like tails of comets. These tails glow in ultraviolet light. As the planet circles its star, the tail sweeps behind, creating structures tens of thousands of kilometers long. These worlds are in the process of disappearing, losing mass over millions of years. Then we discovered planets around the strangest stars, neutron stars, pulsars, white dwarfs. These planets exist in extreme radiation environments. Their atmospheres, if they still exist, would be bombarded with high-energy particles. Some of these planets might be remnants of original worlds. Others might have formed from material after the star died. Their existence defies our expectations of habitability. Now consider planets far beyond the Milky Way. We have detected candidate planets in other galaxies by observing faint distortions in starlight. These extragalactic planets reveal that planetary formation is universal. Even galaxies hundreds of millions of light years away contain worlds. Some may be larger or smaller than anything we know. The universe does not limit itself to familiar patterns. Planetary systems themselves can be strange. Some systems contain dozens of tightly packed planets, others contain only one. Some systems have stable circular orbits. Others contain planets that cross each other's paths. Some systems appear orderly. Others are chaotic. Our solar system is only one example of how planets can organize themselves. It is not the rule. Then there are planets we cannot see at all, but know must exist. Their stars wobble slightly. Their light shifts irregularly. Their gravitational influence reveals their presence, even if no telescope can detect them directly. Many of these unseen worlds may be unusual, small, cold, distant, yet they exist throughout the galaxy. Space reveals something important through its planets. Order is rare. Predictability is limited. Patterns break easily. Each strange planet expands our understanding of how worlds form, move, evolve, and survive. These discoveries show that the universe is not content with simple designs. It produces worlds in every possible combination. In the next part, we move beyond planets entirely and explore the galaxies that behave in impossible ways, galaxies without dark matter, galaxies that shine too brightly, galaxies that appear suddenly in the cosmic timeline, and galaxies that form strange shapes that defy normal physics. Phase 4. The galaxies that should not exist. Galaxies are supposed to follow rules. They form from clouds of gas, gather stars over billions of years, and settle into familiar shapes like spirals or ellipses. They rotate according to the amount of visible matter they contain. They grow through mergers. They fade as their stars age. This is the basic picture we once believed. But the more we observe the universe, the more we realize that galaxies do not behave consistently. Some do things they should never be able to do. Some appear without explanation. Some have no dark matter. Others are made almost entirely of dark matter. Some shine too brightly. Others barely shine at all. These galaxies show us that the universe is not simple. It is full of exceptions. One of the most surprising discoveries ever made was the existence of galaxies with almost no dark matter. Most galaxies behave as if they contain far more mass than we can see. Their stars move too quickly, their rotation curves are too flat, and their structure should fall apart if only visible matter were present. This is why scientists believe dark matter exists. But then we found galaxies like NGC 1052 DF2 and NGC 1052 DF4. These galaxies rotate exactly as expected from the amount of visible matter they contain. They require no dark matter. Their stars move slowly. Their structure makes sense without any invisible mass. This discovery was disturbing because it challenged the idea that dark matter is necessary for galaxy formation. If some galaxies form without dark matter, does that mean dark matter behaves differently in certain environments? Or does it mean our understanding of gravity changes under certain conditions? These galaxies are rare, but their existence forces us to rethink how galaxies grow. They show that the universe is capable of building structures in more than one way. Then we discovered the opposite kind of galaxy, galaxies made almost entirely of dark matter. These galaxies contain very few stars and emit almost no light. They're called ultra-diffuse galaxies. Some are faint, ghost-like structures that drift quietly in the cosmos. Their stars are spread thinly across great distances. Their visible matter is fragile, but their mass is enormous. Something heavy holds them together, and that something can only be dark matter. These galaxies show us that dark matter can dominate a system so completely that stars play almost no role. They also show that galaxies can survive with almost no visible structure. This breaks our assumptions about what a galaxy should look like. It also reveals that the universe is full of invisible architecture, shaped by forces we cannot see. Then there are galaxies that appear far too early in cosmic history. The James Webb Space Telescope revealed galaxies that formed just a few 100 million years after the Big Bang. These galaxies are surprisingly large and bright. They contain stars that should have taken much longer to form. Some appear so massive that our models cannot explain how they grew so quickly. According to existing theories, the early universe did not have enough time or material to build such massive systems. Yet they exist. If these early galaxies are truly as massive as they appear, then our understanding of cosmic evolution may be incomplete. Either galaxies can form much faster than expected, or the early universe behaved differently from how we imagine. These galaxies show that our timeline of cosmic formation may need adjustments. They are reminders that the early universe was more chaotic and more creative than we thought. Then there are galaxies with extremely strange shapes. Some galaxies look like perfect rings with empty centers. Others look like giant question marks, horseshoes, or thin needles. Some look like they have holes punched through them. These shapes come from collisions, gravitational interactions, and tidal forces, but many of them still appear improbable. For example, ring galaxies form when one galaxy passes directly through another, creating a shockwave that ripples outward. This event must be aligned almost perfectly, yet we find ring galaxies throughout the universe. Their existence shows that even rare cosmic events happen often when the scale is large enough. Some galaxies look like long chains of stars. Others appear torn apart, stretched like cosmic ribbons. These galaxies are experiencing tidal disruption. They are being pulled by larger galaxies or clusters, causing their stars to scatter in streams. These tidal structures reveal how galaxies evolve within clusters. They show that galaxies are not isolated, they interact constantly. Their shapes can change over millions of years. They can be stretched, twisted, or even absorbed into larger systems. Then we found galaxies with extremely powerful jets of energy coming from their centers. These jets are produced by supermassive black holes. When matter falls into the black hole, some of it is redirected and expelled at nearly the speed of light. These jets can extend across millions of light years. They heat surrounding gas, affect star formation, and shape the galaxy. In some cases, these jets are so strong that they suppress new star formation for billions of years. These galaxies show that black holes are not quiet passengers in the universe. They control the environment around them. They shape the life cycles of galaxies. They determine whether galaxies grow or fade. But some jets are so powerful that they push the boundaries of what we expect from black holes. They suggest that extreme magnetic fields and unusual conditions can produce more energy than our models predict. Another strange galaxy type is the red nugget. These are compact galaxies filled with old stars. They formed early in cosmic history and stopped growing. They are small, dense, and quiet. Most modern galaxies are much larger. So how did these galaxies freeze in time? Why did they stop evolving? Red nuggets offer clues about galaxy formation, but they also raise questions. They show that not all galaxies follow the same evolutionary path. Some rush through their growth and then stop entirely. Then there are galaxies that behave like giant lenses. They bend light around them because of their mass. This gravitational lensing reveals the presence of dark matter, but some galaxies lens light far more strongly than expected based on visible matter. This mismatch once again points to invisible mass shaping the universe. But lensing also reveals something strange. Some galaxies magnify distant galaxies behind them, making them appear stretched or repeated. These cosmic mirages show how mass bends space-time and how galaxies can distort the appearance of the universe. Another strange discovery is the existence of galaxies with extremely low metallicity. This means they contain almost no elements heavier than hydrogen or helium. These galaxies resemble ancient structures from the early universe, yet some of them exist in the modern universe. Their existence suggests that star formation in these regions happened slowly, preserving their primitive composition. These galaxies act like fossils, showing us what the early universe might have looked like. Then consider galaxies at the edges of clusters. Their shapes are distorted. Their gas is stripped away by high-speed collisions with surrounding material. They fade quickly, leaving behind only stars. Some lose their gas entirely and stop forming new stars. These galaxies show that environment shapes evolution as much as internal processes. A galaxy does not evolve alone. It evolves within a web of forces. Some galaxies shine too brightly. They appear far more luminous than expected given their size. Their stars burn intensely. Some of these galaxies are undergoing starbursts, creating stars at incredible rates. Others contain active black holes that flood the galaxy with radiation. But a few galaxies are bright for reasons we do not fully understand. Their structure, energy output, and composition break expectations. Some galaxies barely shine at all. They contain stars so faint and sparse that they blend into the background. These ghost galaxies drift quietly. They are difficult to detect. They show that the universe contains far more structures than we can see. Many galaxies may exist below our detection threshold. The visible universe may contain only a fraction of the galaxies that are truly there. Then we discovered galaxies orbiting other galaxies like moons. Some small galaxies orbit larger ones in patterns that cannot be explained by simple gravitational models. Their orbits tilt strangely. They form planar structures that appear too organized to be random. These alignments raise questions about the large-scale structure of space and the behavior of dark matter. Now think about galaxies that appear suddenly in our observations. Some seem to blink into visibility. They appear bright for a moment and then fade. This is often caused by transient events like supernova or active black hole phases. But some changes occur too quickly to be explained by known processes. These shifts in brightness challenge our understanding of galactic stability. Galaxies also collide more often than people realize. The Milky Way has consumed many smaller galaxies. Streams of stars across the sky are remnants of past mergers. Some galaxies are currently in the middle of merging. They form twisted structures, long tidal tails, and chaotic star-forming regions. Mergers shape most galaxies in the universe, but some mergers produce shapes so unusual that they look almost unnatural. These structures show that galaxy evolution is violent and ongoing. The strangest galaxies force us to rethink everything. They show that dark matter and normal matter interact differently. They reveal that galaxy growth is not consistent. They suggest that the early universe was more complex than predicted. They expose gaps in our models. They demonstrate that cosmic structures are not as simple as spirals and ellipses. Every strange galaxy expands our understanding of the universe. Each one hints at new physics. Each one reveals features we never expected. Galaxies are not just islands of stars. They are dynamic, evolving, unpredictable systems shaped by gravity, dark matter, energy, and time. In the next part, we will leave galaxies behind and explore the strangest cosmic phenomena, events and signals that do not come from stars or planets or galaxies, but from the behavior of space-time, radiation, and invisible forces. 5. The cosmic phenomena that defy understanding. Space is filled with objects that confuse us, but some of the strangest discoveries are not objects at all. They are events, they are signals, they are behaviors that appear suddenly, last for moments or years, and then disappear again. These cosmic phenomena challenge our understanding of physics because they do not follow predictable rules. They remind us that the universe is not just a collection of stars and galaxies. It is a dynamic environment with processes we are only beginning to understand. One of the most mysterious phenomena is the fast radio burst, or FRB. These bursts appear as intense flashes of radio energy that last only milliseconds. They come from distant galaxies. They carry enormous energy, more than some stars release in days. Most FRBs happen once and never repeat. A few repeat irregularly. Scientists have proposed many explanations: magnetars, neutron star collisions, black hole interactions, or something unknown. FRBs remain one of the strangest phenomena in modern astronomy. They appear suddenly, vanish instantly, and leave almost no trace. Their brief existence forces us to develop theories that accommodate violent, fast, unpredictable cosmic events. Another strange phenomenon is gamma-ray bursts. These are the brightest explosions in the universe. They release more energy in seconds than the sun will release in its entire lifetime. Some gamma-ray bursts come from collapsing massive stars. Others come from neutron star mergers. But some bursts do not fit either category. They last too long or too short. They release energy in unusual patterns. They occur in places where no massive stars should exist. These bursts reveal that the universe has extreme processes capable of producing unimaginable amounts of energy. Then there are cosmic rays. These are high-energy particles that strike Earth from space. Some cosmic rays have energy so enormous that our theories cannot explain how they were accelerated. To reach these energies, a particle would need to be accelerated by forces far beyond anything known in the universe. These particles challenge our understanding of astrophysics. They come from distant galaxies, black holes, or unknown sources. Their energies suggest that the universe contains mechanisms more powerful than any we have identified. Another strange phenomenon is neutrino bursts. Neutrinos are tiny, almost massless particles that pass through matter easily. Most neutrinos come from the sun or cosmic background radiation, but occasionally detectors pick up neutrinos from supernova or distant energetic events. These bursts carry information about processes hidden from ordinary telescopes. They reveal the deep interior of collapsing stars. But some neutrino bursts have unusual energies or directions that do not match known sources. These unexplained neutrinos hint at processes we have not yet discovered. Then there are gravitational waves, ripples in space-time caused by massive collisions. These waves were predicted by Einstein, but detected only recently. Black hole mergers produce clean gravitational wave signals. Neutron-star collisions produce waves combined with electromagnetic bursts. But some gravitational wave detections are unusual. They come from masses heavier or lighter than expected. Some signals suggest mergers between objects that may not be black holes or neutron stars. Some hints even suggest continuous waves from unknown spinning sources. These unexplained signals reveal that the universe contains objects that do not fit neatly into existing categories. Another strange phenomenon is the existence of unexplained periodic dimming in stars. We expect stars to dim when planets pass in front of them, but some stars dim regularly without any visible cause. Some dim in deep cycles over decades. Others dim so dramatically that it looks like something enormous is blocking them, but no object is detected. These dimming patterns may come from dust, unusual star structures, or unknown bodies, but they show that stars can behave in ways that break simple patterns. Space also contains enormous voids, regions with almost no galaxies. Some voids are hundreds of millions of light years wide. Their emptiness is difficult to explain. The distribution of matter in the universe should be more even. These voids suggest that cosmic structure formation may be more complex than our models predict. They reveal patterns in the large-scale structure of the universe that we do not fully understand. Another puzzling phenomenon is the alignment of galaxies across large distances. Some galaxy spin directions appear correlated over vast scales. According to randomness, these orientations should be distributed evenly, but observations show patterns. This hints at unknown influences in the early universe. It may be connected to cosmic inflation, dark matter distribution, or something deeper. Then there is the cosmic microwave background, a faint glow left over from the Big Bang. This radiation should be incredibly smooth, but it contains tiny irregularities. These irregularities are expected, but there are larger, unexplained patterns as well. One is the cold spot, a region cooler than its surroundings. Its size and intensity are difficult to explain with standard models. It could be a statistical anomaly, or it could indicate something unusual, like a giant void or a feature left from early cosmic processes. Another strange phenomenon is the WOW signal. This burst of radio energy detected in 1977 lasted only seconds. It was strong and narrowband, something natural processes rarely produce. It came from a region of space with no known objects. Multiple attempts to detect it again have failed. It remains a single, unexplained event. Whether natural or artificial, The wow signal is one of the strangest signals we have ever recorded. Space also contains phenomena that last far longer. For example, there are repeating patterns in radio emissions from distant galaxies. Some repeat every 16 days, others every few months. These signals are not predictable enough to be caused by rotation alone. They may involve binary stars, magnetars, or interactions with surrounding gas, but their regularity and strength remain unusual. Then consider supermassive black hole flares. Black holes are usually quiet and less feeding, but sometimes they flare dramatically, shining brightly for a short period. These flares come from gas being compressed or torn apart near the event horizon, but some flares appear without clear feeding events. Some are too bright, too fast, or too frequent. These anomalies show how unpredictable black hole environments can be. We also found stars that emit lasers, natural lasers called astrophysical masers. These occur when atoms in star-forming regions amplify microwaves. Some regions emit incredibly intense masers, far more powerful than theoretical predictions. These signals reveal conditions deep inside molecular clouds and around dying stars. Yet their strength and precision remain surprising. Another phenomenon is stellar oscillation. Many stars vibrate, producing waves that travel through them. These vibrations allow scientists to study their interiors, but some stars oscillate in unexpected ways. They produce frequencies that should not exist. Their internal structures appear more complex than models allow. These anomalies show that star interiors are not simple spheres. Then there are rotating radio transients. These are brief irregular radio pulses from neutron stars. They are not regular like pulsars. They flash unpredictably. Some go silent for months or years. Their behavior challenges our understanding of neutron star magnetism and rotation. Another surprising discovery is cosmic jets from young stars. These jets fire out material at high speeds, shaping surrounding gas, but some jets twist, bend, or pulse in unusual ways. These patterns suggest that star formation is more chaotic than we believed. Magnetic fields, rotation, and turbulence combine to produce strange structures. Space also contains strange reflective phenomena. Light echoes occur when light from a bright event reflects off distant dust clouds. These echoes allow us to see repeated versions of past events, but some light echoes appear unexpectedly or show structures that do not match expected dust patterns. These phenomena reveal hidden features of interstellar space. Then there are high-velocity clouds, enormous blobs of gas moving through the galaxy at speeds far too high for simple explanations. Their origins remain uncertain. They may come from galactic fountains, interactions with dark matter, or remnants from ancient collisions. Their motion suggests that the galaxy contains unseen forces shaping its structure. Another phenomenon is the existence of extremely faint galaxies called ultra-faint dwarfs. These galaxies contain very few stars, but enormous amounts of dark matter. Their existence is puzzling. They should not have enough mass to hold themselves together, yet they survive. These galaxies reveal the role dark matter plays in the smallest cosmic structures. Then consider cosmic magnetism. Magnetic fields exist everywhere in space, around stars, planets, galaxies, and even in intergalactic space. But the origin of these magnetic fields remains mysterious. Some regions contain unexpectedly strong fields, others contain almost none. Magnetic fields shape cosmic evolution, but we still do not understand how they formed in the early universe. All these phenomena share one theme. The universe behaves in ways that challenge our theories. Some events are too fast, some are too powerful, some are too faint, some are too consistent, some are too unpredictable. Each phenomenon forces science to improve. Each anomaly reveals gaps in our understanding. Each mystery is a doorway to deeper knowledge. The universe does not reveal itself gently. It speaks in bursts, flares, waves, and patterns. It surprises us constantly. In the next part, we explore one of the strangest categories of discoveries, objects that exist in impossible states of matter, including neutron stars, quark stars, and other ultra-dense creations of the universe. 6. The objects made of impossible matter. Space contains objects made of materials that should not exist. These objects are formed under conditions so extreme that atoms collapse, particles rearrange, and matter enters states that break the rules of everyday physics. These states do not appear on Earth. They do not appear inside planets or stars like the Sun. They exist only in the universe's most violent environments. When massive stars die, the pressure becomes so high that matter begins transforming into new structures. These structures lead to neutron stars, magnetars, quark stars, and perhaps even stranger objects still waiting to be discovered. A neutron star is one of the universe's strangest creations. When a massive star collapses, its core compresses so tightly that electrons are forced into protons, turning them into neutrons. The result is a sphere only about 20 kilometers wide, but containing more mass than the Sun. A teaspoon of neutron star material would weigh more than a mountain. This density creates gravitational fields strong enough to bend light dramatically. Neutron stars rotate rapidly, sometimes hundreds of times per second, and emit beams of radiation from their magnetic poles. These beams produce the pulsing signals we call pulsars. The interior of a neutron star is not fully understood. At the surface, the matter is crushed into a solid crust of neutron-rich nuclei. Beneath the crust lies a sea of neutrons behaving like a liquid. Deeper still, neutrons might break down into individual quarks, but no one knows exactly what happens at these densities. It is possible that neutron stars contain exotic phases of matter not found anywhere else. These phases might involve superfluid neutrons, superconducting protons, or entirely new particles. Even stranger than neutron stars are magnetars. A magnetar is a neutron star with a magnetic field trillions of times stronger than Earth's. This magnetic field is so powerful that it can warp atoms, break chemical bonds, and distort the vacuum of space. Magnetars sometimes produce giant flares, bursts of energy so strong they can affect other stars thousands of light years away. One magnetar flare in 2004 slightly altered Earth's upper atmosphere, despite being extremely distant. Magnetars form when a collapsing star spins unusually fast and channels energy into its magnetic field. But the exact conditions that produce magnetars remain unclear. Some magnetars appear to be born spinning rapidly, while others form after a supernova with slower rotation. Their internal structures may contain exotic phases of matter influenced by the extreme magnetic field. These objects show that the universe can twist physical laws to their extreme limits. Another possible type of object is the quark star. If the pressure inside a collapsing star becomes high enough, neutrons may break down into individual quarks, the fundamental particles that make up protons and neutrons. A star made of quark matter would be even denser than a neutron star. Its interior would form a strange soup of free quarks moving freely. Some theories propose that quark stars may have surfaces made of exotic crystals or fluid-like structures, but no quark star has been confirmed because their properties are difficult to distinguish from ordinary neutron stars. However, some unusually small or unusually dense neutron stars may be quark star candidates. Even more exotic than quark stars are hypothetical strange stars. These objects would contain strange quarks, a heavier version of the quarks found in ordinary matter. Strange quark matter might be stable under extreme pressure. If so, strange stars could exist. They would be incredibly dense and behave unlike any known object. Strange matter might even be able to convert normal matter into strange matter upon contact. This idea remains theoretical, but shows how far the universe might push physical laws. Another mysterious possibility is the existence of boson stars. These hypothetical stars would not be made of normal matter. Instead, they would be composed of bosons, particles that follow different rules than ordinary matter. Boson stars would be transparent, nearly invisible, and would not emit light. Their mass could produce gravitational effects similar to black holes, but they would lack event horizons. Some phenomena currently attributed to black holes could theoretically be caused by boson stars, though there is no evidence yet. These objects would require new physics to explain their stability. There is also the possibility of preon stars, even more speculative structures composed of particles smaller than quarks. If quarks are made of smaller constituents called preons, then stars made of preon matter could exist. These stars would be incredibly dense, possibly smaller than a meter across, but containing more mass than a mountain. This idea pushes the limits of theoretical physics. Whether preons exist is still unknown, but the concept shows how deep the universe's structure might go. Another strange possibility is the existence of dark stars. Stars powered not by nuclear fusion, but by dark matter interactions. In the early universe, when dark matter density was higher, clouds of hydrogen might have collapsed into stars heated by dark matter annihilation. These dark stars would be far larger than normal stars and shine faintly from dark matter energy. They might not look like stars. They might glow in unusual wavelengths. If such stars existed, they could explain some of the unusually bright objects observed by the James Webb Telescope. But the idea remains speculative. Then there are white dwarfs, stars that have exhausted their fuel and collapsed into dense, Earth-sized objects. Their interiors are made of electron-degenerate matter, where electrons are packed tightly to resist further collapse. But white dwarfs become stranger as they cool. Over billions of years, their interiors crystallize. A white dwarf can become a giant diamond floating in space. This process reveals that even dead stars undergo unusual transformations. Some white dwarfs behave unpredictably. They spin rapidly, flare unexpectedly, or display magnetic fields stronger than predicted. Some show atmospheric compositions that defy explanation. Heavy elements that should sink into their interiors remain floating in their atmospheres. This suggests ongoing interactions with surrounding material or unknown processes happening inside the star. Another unusual object is the Thornjitkov object. This rare type of star occurs when a neutron star falls into a red supergiant. Instead of destroying the larger star, the neutron star sinks into its core. The result is a hybrid object, part star, part neutron star. These objects burn material differently and produce unusual chemical signatures. Very few candidates exist and none have been confirmed with complete certainty. If they do exist, they represent one of the strangest stellar interactions possible. Then we have supernova remnants, the debris left after massive stars explode. These remnants contain shock waves, high-energy particles, and expanding shells of gas. Some remnants contain structures that behave unpredictably. Jets, filaments, and arcs appear that do not match simple models. These chaotic structures show how energy moves through space in complex ways. They also reveal how elements are created and dispersed. Another strange structure is the Black Widow pulsar. This neutron star orbits extremely close to a small companion star. Its radiation is so intense that it slowly evaporates its companion. The neutron star consumes the material like a predator. Over time, the companion may be completely destroyed, leaving only the pulsar behind. These systems show how violently neutron stars interact with nearby objects. Now consider the objects at the edge of collapse. Some stars hover between becoming neutron stars and black holes. They may have exotic cores containing hyperons, particles heavier than neutrons. These stars behave strangely. Their masses and radii do not match predictions. Their internal structure may include layers of exotic matter. They represent a transition between ordinary matter and extreme gravity. The existence of these extreme objects shows that the universe produces matter under conditions we cannot replicate. It compresses particles until they form new structures. It bends physics into unfamiliar shapes. These objects teach us about the limits of matter, the behavior of particles, and the role of gravity. Every strange object comes from conditions that push nature to its extremes: high pressure, high density, high gravity, extreme magnetism, rapid rotation. These conditions create environments where new states of matter emerge. The universe behaves differently when pushed to its limits. These objects matter because they reveal what happens when physical laws operate under extreme conditions. They show us how matter behaves when atoms collapse. They show us how particles behave when their structure breaks down. They show us how gravity shapes matter at densities far beyond anything humans can create. In the next part, we shift from extreme matter to the strangest signals we've ever received: radio bursts, unexplained transmissions, repeating patterns and mysterious noises that reach us across cosmic distances. 7. The signals that should not exist. Space is mostly silent, yet every so often the universe sends signals that do not fit into any category we understand. These signals come as short bursts, long pulses, repeating patterns, and one-time events that appear for a moment and disappear forever. Some signals come from known objects, behaving in strange ways. Others come from regions where nothing visible exists. Some repeat. Others arrive once and never again. These signals remind us that the universe has channels we are only beginning to detect. They show that space communicates through energy, radiation, and patterns that stretch across billions of light years. One of the strangest signals ever detected is the fast radio burst. These bursts are brief but incredibly powerful flashes of radio energy that last only a few milliseconds. Their brightness suggests they come from distant galaxies. Their intensity suggests they come from extremely energetic sources. Yet most FRBs are one-time events. They appear in the data for an instant and never return. But a few FRBs repeat. Some repeat in irregular patterns. Others repeat in cycles, where bursts appear every few days, then pause for weeks, then repeat again. The repeating bursts behave differently from the one-time bursts. This division suggests that FRBs may come from several different types of sources, or from processes we do not fully understand. Some FRBs look like they come from magnetars. Others seem too powerful to fit magnetar models. Some FRBs come from galaxies with active star formation. Others come from quiet regions. Some are narrow and crisp, others are wide and messy. This variety shows that FRBs are not a single phenomenon. They are a category of signals that points toward deeper mysteries. FRBs challenge our understanding because they require extreme energy, extreme speed, and extreme precision. Only the universe's most violent objects can produce such signals, yet their origins remain uncertain. Another strange signal is the long-duration radio burst. Unlike FRBs, these signals last for minutes or even hours. They appear unexpectedly and fade slowly. Some come from known objects like neutron stars. Others come from places where nothing is visible. One of the strangest discoveries is a repeating radio burst near the centre of the Milky Way. It turns on for several minutes, shuts off for long periods, and repeats in ways that do not match any known process. It is too faint to be a pulsar. It does not behave like a magnetar, and it appears in a region full of complex gravitational effects. This repeating burst shows how little we know about the radio sky. Then there is the WOW signal, one of the most famous unexplained signals in history. In 1977, a radio telescope in Ohio detected a sharp, intense burst from deep space. The signal lasted only 72 seconds. It came from a direction that contained no known stars or planets bright enough to explain it. The astronomer who found it wrote, "Wow," next to the data printout. Despite many attempts, the signal has never been detected again. It could have been a natural event, an unusual alignment, or something else entirely, but its strength and clarity remain unexplained. The WOW signal represents one of the universe's most mysterious moments, a single burst that refused to return. Another strange signal involves unusual X-ray emissions from galaxy clusters. These emissions appear as faint lines that do not match known atomic signatures. One possibility is that they come from the decay of dark matter particles. If true, these X-ray lines could be the first direct evidence of dark matter interacting with visible matter. But other explanations exist, and the signals remain debated. They show that the universe contains energies and interactions we have not fully mapped. Then there are the repeating radio pulses from unusual neutron stars. Some neutron stars produce bursts that turn on and off in long cycles. They behave like pulsars, but with irregular timing. They pulse for months, disappear for years, then pulse again. Their behaviour suggests that something inside these neutron stars changes over time, affecting the magnetic field and the radiation they emit. These changes challenge simple models of neutron star interiors. They suggest complex layers and shifting structures. Another strange category of signals comes from the centre of the Milky Way. The region around the supermassive black hole emits radio waves, X-rays and infrared signals that fluctuate unpredictably. Some signals appear as small flares, others appear as sudden increases in brightness. These flares do not always correspond to visible matter falling into the black hole. Sometimes they happen with no clear cause. These irregular signals suggest that the environment near the black hole is far more dynamic than we thought. Space also contains soft gamma repeaters, objects that emit repeated bursts of gamma rays. These bursts can vary in intensity and frequency. Some are extremely powerful, others are faint and irregular. Many soft gamma repeaters are magnetars, but not all magnetars produce them. The behaviour depends on internal magnetic stresses that build and release energy. These signals show how magnetic fields shape stellar interiors. Then there are signals that come from deep cosmic voids. Some radio signals arrive from regions with no visible galaxies. These signals are rare, but their existence suggests that either faint galaxies exist beyond detection limits, or that unknown sources emit radio waves in empty space. Both possibilities point toward gaps in our understanding. Another strange signal involves the hydrogen line, a radio emission from neutral hydrogen atoms. Scientists observe this line to map the galaxy, but some regions show unexpected variations in intensity or shape. These variations may indicate unusual structures in the interstellar medium or interactions with dark matter. The hydrogen line reveals how gas moves and clumps, but it also exposes irregularities that defy explanation. We also detect mysterious signals from variable stars. Some stars produce radio emissions that change rapidly. Others emit X-rays or ultraviolet bursts that appear without warning. These emissions suggest complex magnetic interactions inside the stars, but in many cases the patterns do not match any known magnetic cycle. Cosmic microwave background anomalies also act like signals. The CMB contains slight temperature fluctuations that reveal the early universe's structure, but some patterns, like the cold spot or certain symmetrical alignments, remain difficult to explain. These patterns behave like signals from the universe's past. They may contain information about early cosmic inflation or quantum effects imprinted on space-time. Another category of strange signals comes from gravitational waves. Most detected gravitational waves come from black hole or neutron star mergers, but some candidates do not match known templates. They may represent unusual collisions or exotic systems we have not modelled. Some signals seemed continuous, suggesting rapidly spinning objects with slight irregularities, but these continuous sources remain unconfirmed. If real, they could point to exotic neutron star structures or unknown binary systems. Then there are cosmic radio circles. These giant faint rings of radio light appear around certain galaxies. They look like boundaries or shockwaves, but their origin is unclear. They behave like signals frozen into space, marking past energy releases. These rings challenge our understanding of radio emissions on galactic scales. Another strange phenomenon is unexplained periodicity in some FRBs. One FRB repeats in cycles of 16 days. Burst activity increases, then stops, then begins again. This pattern suggests orbital behaviour or rotational cycles, but no known object fits the pattern perfectly. Another FRB shows a cycle of 157 days. The existence of cycles in such powerful bursts suggests that some repeating FRBs may involve binary systems, precessing magnetars, or unknown periodic forces. Some signals come from planets as well. Exoplanets interacting with their stars can produce radio emissions, but some emissions do not match expected interactions. They appear too strong or too irregular. These emissions could come from magnetic storms, star-planet interactions, or unknown atmospheric processes. Then there are signals that appear as noise but contain structure upon closer examination. Some of these signals may come from distant pulsars scattering through turbulent gas. Others might come from unknown repeating processes, but a few remain unexplained even after years of study. They suggest that the universe contains sources with patterns we are not yet able to identify. Another strange signal type is the X-ray heartbeat. These heartbeat signals come from black hole systems where matter falls inward in cycles. The system brightens, dims, and brightens again with regular rhythm. Some heartbeat patterns are stable, others drift slowly. A few heartbeat signals behave in ways that break simple accretion models. These signals reveal the complexity of matter spiraling into black holes. All of these signals share a common theme. They do not behave consistently. They appear unexpectedly. They demand explanations we do not yet have. Signals from space are not random noise. They carry information about extreme environments, unusual objects, and hidden processes. Each unexplained signal pushes us to refine our models. Each pattern challenges our assumptions. Each anomaly forces science forward. The strange signals of the universe show how much we still cannot hear. Our instruments are sensitive, but the universe's voice is far more complex. With every improvement in technology, new signals appear, signals that redefine what we thought was possible. In the next part, we explore the strangest cosmic structures ever seen, including rings, bubbles, filaments, arcs, and the enormous shapes that stretch across millions of light years. 8. The cosmic structures. Too large to believe space contains objects that are strange, but it also contains structures that are so large they should not exist. These are not stars, not planets, not even galaxies. These are formations made of millions of galaxies. They stretch across unimaginable distances, sometimes billions of light years. They form patterns that appear too organized for a random universe. They look like they were arranged rather than formed by chance. These enormous structures force us to question how matter spreads across the universe. They challenge our ideas of cosmic uniformity. They show that the universe is far more structured and far more extreme than we thought. One of the strangest structures ever discovered is the large quasar group, known as the huge LQG. It stretches more than 4 billion light-years across. According to standard cosmology, structures this large should not exist because the universe is supposed to be uniform beyond certain scales. But the huge LQG breaks that rule. It contains more than 70 quasars linked together in a chain-like structure. Their positions cannot be explained by simple random clustering. Something about the early universe allowed matter to form structures far larger than expected. Another massive structure is the Hercules Corona Borealis Great Wall. This is one of the largest known structures in the universe. It spans roughly 10 billion light-years. That means it covers about a tenth of the observable universe. It was detected through gamma-ray bursts, which clustered in a pattern too large to fit our current models of cosmic structure formation. The existence of this wall challenges the idea that the universe is roughly the same everywhere on very large scales. Instead, it suggests large-scale anisotropy, meaning some directions in the universe contain more structure than others. Then there are cosmic filaments, long, thin threads of galaxies and dark matter that form the backbone of the cosmic web. Filaments stretch for hundreds of millions of light-years. They connect galaxy clusters like highways. They guide the flow of matter across space. Some filaments contain dense clusters. Others are quiet streams of dark matter. These filaments form the largest continuous structures in the universe. But some filaments behave strangely. They twist, they loop, they bend toward empty regions. Their shapes suggest complex gravitational interactions, but their scale is so large that modelling them remains difficult. Between filaments lie cosmic voids, enormous empty regions with almost no galaxies. Some voids span hundreds of millions of light-years. Their emptiness is puzzling. Matter should spread more evenly across the universe. Yet these voids contain only a fraction of the expected galaxies. Some astronomers believe voids form through gravitational effects pushing matter outward. Others suggest early fluctuations in density created these vast empty spaces. But the true cause remains uncertain. Another strange cosmic structure is the Sloan Great Wall, a massive arrangement of galaxies stretching over 1 billion light-years. It was one of the first discoveries that challenged the idea of cosmic uniformity. The Sloan Great Wall is too large to form naturally under simple models of gravity and dark matter. It suggests that early density fluctuations were far more significant than predicted. Then there is the Giant Ring, a circular structure discovered through the distribution of gamma-ray bursts. It spans more than 1 billion light-years and forms an arc-like shape. Circular arrangements at this scale are difficult to explain. Gravity does not naturally produce perfect rings on cosmic scales. The Giant Ring may be a projection of a larger three-dimensional structure. It may be a relic of early universe physics, or it may be something we do not yet understand. Its regular shape is what makes it so strange. Another structure is the enormous Big Ring, discovered recently. This ring-like formation spans more than 1.3 billion light-years. Its shape resembles a loop or cosmic arc. Structures this large violate current models of cosmology. They suggest that something unexpected may have influenced matter distribution in the early universe. The existence of two massive ring-like structures, the Giant Ring and the Big Ring, raises even more questions. Cosmic bubbles also form strange structures. One well-known example is the Fermi bubbles, two giant lobes of gamma-ray emission extending above and below the Milky Way's centre. These bubbles stretch tens of thousands of light-years. They appear to have formed from a massive burst of energy, possibly from the supermassive black hole at the centre of the Milky Way. Their shape and symmetry are unusual. They suggest that our galaxy has undergone dramatic events in its past. Then there are radio bubbles, giant spherical shells around galaxies that emit strong radio waves. Some of these bubbles come from black holes feeding on surrounding matter. Others may come from starburst winds. But their sizes and energies often exceed expectations. They show that galaxies can shape their surroundings on enormous scales. Another strange structure is the ORC, the Odd Radio Circle. These huge circles of faint radio emission appear around distant galaxies. They are massive, spanning hundreds of thousands of light-years. But they do not match known structures like supernova remnants or galaxy jets. Their circular shape suggests a shockwave expanding outward. But the cause of the shockwave is unknown. ORCs are recent discoveries, and each new one raises more questions. Cosmic arcs are another category of strange structures. These arcs appear as curved lines of light created by gravitational lensing, light bending around massive structures like galaxy clusters. But some arcs are unusually large, bright, or distorted. They suggest that the distribution of dark matter in those clusters is not uniform. Sometimes the arcs appear in places where no massive object is visible. These unexplained arcs point toward invisible mass concentrations. Then there are Einstein rings, perfect circles of light created when a galaxy aligns precisely with a more distant object. These rings are rare because the alignment must be exact, but the existence of Einstein rings shows how gravity bends light across incredible distances. Some rings are almost perfect circles, others are warped or incomplete. These distortions reveal the shape of space-time in those regions. Another enormous structure is the Shapley supercluster, one of the densest regions in the local universe. It contains thousands of galaxies. Its mass pulls other galaxies toward it, influencing motions across hundreds of millions of light-years. Our Milky Way is drifting toward the Shapley region, because of its immense gravitational pull. This drift suggests that the universe contains directional gravitational forces that shape galaxy movement on large scales. Then we discovered the Great Attractor. This mysterious region pulls galaxies toward it, including the Milky Way. But it is hidden behind dense dust clouds, making it difficult to observe. The Great Attractor may be a massive cluster, a filament, or something else entirely. Its gravitational influence affects galaxies across hundreds of millions of light years. Yet we still do not fully understand what lies within it. Another strange structure is the dipole repeller, a region that appears to push galaxies away. Combined with the Great Attractor's pull, these forces shape the motion of galaxies across the local universe. The existence of a repelling region is puzzling. Gravity only pulls, but matter distribution can make regions appear to repel as galaxies move toward denser areas. This interplay creates a cosmic flow pattern, unlike anything predicted by simple models. Then there are cold spots in the cosmic microwave background. One of these cold regions is unusually large, spanning hundreds of millions of light years. The temperature difference is small but meaningful. Some believe the cold spot may be a supervoid, a region with unusually low galaxy density. Others think it could be a leftover imprint from early universe processes. Its structure and shape remain unexplained. The cosmic web itself is the largest structure of all. It consists of filaments, clusters, walls, and voids woven together across billions of light years. Galaxies lie along these filaments, like beads on a string. Dark matter forms the framework. Gravity shapes the nodes where filaments meet. Yet the cosmic web forms patterns that appear surprisingly organized. The repeating grid-like structure suggests deeper rules about how matter spreads through space. But some patterns in the cosmic web look too regular to be random. Alignments, repeating densities, parallel filaments. These features hint at underlying processes we do not yet understand. The universe may contain rules of structure formation that go beyond simple gravity, or it may reflect early quantum fluctuations amplified across time. These enormous structures force us to rethink what large means. They stretch across distances so vast that light takes billions of years to travel from one end to the other. They show that the universe forms shapes at scales we never imagined. They reveal the influence of dark matter and dark energy. They expose the deep architecture of cosmic evolution. Every strange structure tells a story about the universe's past. Some formed through collisions, some formed through gravitational collapse, some formed through early cosmic expansion, and some remain mysteries waiting for new physics. In the next part, we explore the strangest movements in space, objects flying too fast, spinning too wildly, drifting away from everything, or behaving in ways that violate expected dynamics. 9. The movements that should not be possible. Motion in the universe should follow rules. Stars orbit their galaxies, planets orbit their stars. Galaxies drift slowly apart as the universe expands. This is the simple picture we expect. But when we measure the actual movements in space, we find objects that move too fast, too slow, or in directions that make no sense. Some drift through space alone. Some spin at impossible speeds. Some accelerate when nothing should push them. Some face gravitational forces that should tear them apart, but don't. These movements reveal that the universe is not as stable or predictable as it appears. Space is full of motions that break the rules. One of the strangest types of motion comes from hypervelocity stars. These are stars moving so fast that they escape their galaxies. Most stars move at moderate speeds, orbiting their galactic centres, but hypervelocity stars can travel at millions of kilometres per hour. Their speeds are so high that the Milky Way cannot hold them. They are being ejected into intergalactic space like bullets. Some of these stars were flung out after interacting with the supermassive black hole at the centre of the Milky Way. Others were ejected when their binary partner exploded as a supernova. A few may have been accelerated by three-body gravitational interactions in dense clusters. These stars show that the galaxy is not a calm environment. It can launch stars into the darkness with enough force to send them drifting for billions of years. Then there are runaway stars, stars that move far faster than expected but still remain in the galaxy. These stars may have been part of binary systems where one partner exploded. The explosion acts like a slingshot, sending the surviving star hurtling forward at high speed. But some runaway stars show speeds too high for this explanation. Their motion suggests additional forces at work. These stars reveal chaotic interactions that happen deep inside star clusters where the density of stars is extreme. Another strange category involves stars orbiting black holes at impossible speeds. Near the centre of the Milky Way, the S-stars orbit the supermassive black hole with incredible velocities. One star, S2, completes its orbit in only 16 years, despite being thousands of astronomical units away. At closest approach, it reaches speeds greater than 5,000 kilometers. These stars confirm Einstein's theory of relativity. Their orbits bend, shift, and precess in ways predicted by space-time curvature. But they also show how extreme gravity shapes motion in ways no normal planetary system experiences. Then there are galaxies that move strangely. Some galaxies travel through space much faster than expected. Their high velocities suggest that gravitational structures outside their visible region influence them. The Great Attractor pulls galaxies from one direction, while the dipole repeller pushes them from another. This creates unusual flows of galaxies across hundreds of millions of light years. These flows do not match simple expansion models. They suggest large-scale mass concentrations and voids affecting motion across enormous distances. The Milky Way itself moves through space at more than 2 million kilometers per hour, drifting toward the Virgo cluster and the Shapley supercluster. These motions reveal that the universe's structure is not uniform. The galaxy is responding to gravitational forces from massive regions we can see, and perhaps some we cannot. Motion at these scales hints at deeper cosmic structures, including dark matter distribution. Another strange movement comes from galaxies that rotate too fast. The outer edges of galaxies move at nearly the same speed as their inner regions. According to standard physics, this should tear the galaxy apart, yet the stars remain in orbit. This behaviour led to the discovery of dark matter. But even after decades of study, some rotation curves still challenge our models. Some galaxies rotate in patterns too smooth or too sharp to fit predictions. Others show dips or spikes in velocity with no visible explanation. These irregularities suggest that dark matter may not behave the same way everywhere. Then there are galaxies moving backward, rotating in the opposite direction of their stars or gas. Some galaxies contain outer rings of stars that orbit opposite the inner regions. These counter-rotating structures suggest past collisions or mergers, but in some cases no evidence of mergers exists. These galaxies show that angular momentum can reverse under certain unknown conditions. Another strange motion involves galaxies that appear to be drifting toward empty space. Instead of moving toward dense clusters, some galaxies accelerate toward voids. This seems impossible. gravity should only pull toward matter, not emptiness, but the movement may be an illusion caused by galaxies being pulled away from voids by surrounding structures. Even so, the pattern looks like motion toward nothingness. This inversion challenges our understanding of gravity and cosmic flows. Now consider dwarf galaxies orbiting the Milky Way. Their orbits are strangely aligned. Many follow similar planes instead of random paths. This unexpected organization suggests that dwarf galaxies may have formed together or were drawn into a shared pattern by larger cosmic forces. Standard models predict that orbits should be chaotic, but observations show surprising order. Some galaxy clusters also move unusually. They collide at speeds that models say should be impossible. The Bullet cluster is one of the most famous examples. Two clusters collided at enormous velocity, separating visible matter from dark matter. This separation revealed that dark matter passes through itself with little interaction. But the speed of the collision challenges formation models. Other clusters show similar extreme velocities. These motions suggest that early cosmic expansion or unknown gravitational effects influenced cluster movement. Another strange movement involves objects called binary black holes. These pairs orbit each other as they spiral inward. Their orbital decay produces gravitational waves. Most systems behave as expected, but some show motions that deviate slightly from predictions. These deviations might reveal new physics or complex interactions with surrounding gas. Binary black hole motion remains one of the most precise tests of gravity. Then there are the motions of interstellar objects passing through our solar system. The first known example was Oumuamua, an elongated object moving too fast to be bound to the Sun. It entered the solar system at high speed, passed close to the Sun, and left again on a hyperbolic trajectory. It also accelerated slightly without any visible gas or dust. This unusual motion sparked numerous theories, from natural explanations to more speculative ones. The second interstellar object, Comet Borisov, behaved more normally, but still revealed that interstellar visitors are more common than expected. Asteroids and comets within our solar system also move strangely. Some objects show sudden changes in speed or direction without clear causes. These changes may come from uneven outgassing, impacts, or internal stresses, but a few anomalies remain unexplained. Their motion raises questions about hidden forces in the solar system or unusual material properties. Another example of strange movement is planets with extremely tilted orbits. Uranus rotates nearly on its side. Its tilt suggests a past collision, but no clear evidence exists. Exoplanets show even stranger tilts. Some orbit in polar directions, travelling above or below their star's equator. A few even orbit backward relative to the star's rotation. These extreme tilts reveal violent histories and chaotic interactions in planetary systems. Now think about stars near black holes. Their orbits become distorted by relativity. Time dilation affects their motion. Their paths are not simple ellipses, but precessing shapes. These motions test the limits of physics. Some stars experience gravitational redshift as they approach the black hole, changing their observed light. These changes confirm predictions, but also highlight the complexity of motion in curved space-time. Motion becomes even stranger near neutron stars. Their gravitational fields can accelerate nearby matter to extreme speeds. Some neutron star systems eject material at near-light speeds. Jets of plasma shoot out in narrow beams. Accretion disks spin rapidly around them. These movements involve magnetism, gravity, and high-energy processes combined in ways that create unpredictable behavior. Then there are tidal interactions within galaxies. Stars near galactic centers orbit rapidly. Gas clouds stretch into long streams. Tidal forces tear apart smaller galaxies. These motions create structures like stellar streams, long lines of stars pulled from dwarf galaxies being consumed by larger ones. These streams reveal the unseen shape of dark matter. Around galaxies, another strange type of motion appears in galaxy mergers. When two galaxies collide, their stars rarely hit each other. Instead, gravity reshapes their orbits. Some stars get flung far outward, others fall inward. Gas clouds collide, triggering star formation. Black holes at the centers spiral closer until they merge. These complex motions create chaotic yet beautiful structures. The process takes millions of years, but the end result is often a larger galaxy with a new shape. Cosmic expansion itself is a strange form of motion. Galaxies move away from each other, not because they're traveling through space, but because space is expanding between them. Some galaxies move away faster than the speed of light. This does not violate physics because they're not moving through space. Space itself is stretching. This movement reveals the influence of dark energy, which accelerates cosmic expansion. The acceleration affects motion at the larger scales. Some galaxies appear to be gaining speed faster than expected. This could indicate variations in dark energy across space, or it could be measurement error. But if true, it suggests that cosmic expansion is not uniform. Another surprising discovery involves stars oscillating within galaxies. Stars do not orbit in perfect flat planes. They move up and down through the galactic disk like waves. These oscillations may be caused by past mergers or interactions with dark matter clumps. The vertical motion of stars reveals hidden structures in the galaxy. All these strange motions show that the universe is not calm. It is full of objects being pushed, pulled, accelerated, spun and flung across space. Every unexpected movement reveals something deeper. Every anomaly forces us to rethink gravity, formation, and cosmic structure. Motion is a language. The universe speaks through how objects move. When an object moves strangely, it is telling us something important. It is revealing invisible forces, hidden structures, or unknown physics. In the next part, we explore the strangest energies and forces in space, including dark energy, cosmic acceleration, antimatter imbalance, and the unexplained pressures shaping the universe. 10T. The energies and forces that rewrite the universe. The universe is held together and shaped by forces we can measure, but some of the strangest discoveries in modern science come from forces and energies we do not fully understand. Gravity, electromagnetism, and nuclear forces explain much of what we see, but space contains mysteries that do not fit neatly into any category. Some forces push the universe apart, some seem to hide in empty space. Some appear to work against matter. Others influence the behavior of galaxies, clusters, and cosmic expansion. These energies shape everything, yet much about them remains unknown. Understanding them is one of the biggest challenges in modern physics. One of the strangest forms of energy in the universe is dark energy. Dark energy is the force causing the universe to expand faster over time. For decades, scientists believed that expansion would slow down due to gravity, but observations showed the opposite. Distant galaxies appear to be moving away faster than closer ones, and the rate of expansion is increasing. This means some unknown energy is acting across all of space, pushing everything apart. And it isn't a small influence. Dark energy makes up about 70% of the universe. That means most of the universe is something we cannot see, measure directly, or understand. Dark energy may be a property of space itself. It may be related to quantum fluctuations. It may be something entirely new. No one knows for sure. The simplest explanation is the cosmological constant, an energy built into empty space. But other explanations involve dynamic fields that change over time. Whatever dark energy truly is, it determines the future of the universe. If it continues increasing, galaxies will eventually move so far apart that even the closest ones become unreachable. If it changes in strength, the universe's future could be far stranger. Dark energy is the force that governs the larger scales of reality, yet we cannot detect it except through its influence. Then there is dark matter, a form of invisible matter that does not interact with light. Dark matter does not reflect, absorb, or emit radiation. It interacts only through gravity, and yet it holds galaxies together. Without dark matter, stars in the outer regions of galaxies would fly off into space. Without dark matter, galaxy clusters would not stay bound. Without dark matter, the cosmic web itself would not have formed. Dark matter shapes the universe on every scale, larger than solar systems. But despite its influence, we have never detected a dark matter particle directly. We know it exists because of gravitational effects, but we cannot identify its properties. It may be made of weakly interacting massive particles. It may be made of axions. It may be something even stranger, ultralight particles, hidden dimensions, or a form of matter that behaves collectively rather than individually. Some theories even suggest dark matter might be made of primordial black holes, formed right after the Big Bang. The truth remains unknown. Dark matter is one of the strangest discoveries because it is everywhere, yet invisible. Another strange energy is found inside neutron stars. Their interior contains forces that break normal physics. At these densities, neutrons behave like a superfluid, a liquid with no friction. This superfluid can move endlessly without losing energy. Neutron stars also contain superconducting regions where charged particles flow with zero electrical resistance. These states do not exist naturally on Earth. They show that matter can behave in ways we never see under normal conditions. The forces inside neutron stars combine nuclear physics, quantum mechanics, and relativity in extreme ways. Their behaviour hints at new forms of matter we cannot create in the lab. Now consider antimatter. Antimatter is identical to normal matter, but with opposite charge. When matter and antimatter meet, they annihilate and release energy. The laws of physics suggest that the early universe should have produced equal amounts of matter and antimatter, but it did not. Instead, almost all antimatter disappeared, leaving a universe made almost entirely of matter. This imbalance is one of the strangest mysteries in cosmology. Something in the early universe favoured matter over antimatter. Whatever caused that imbalance shaped everything: stars, planets, life, and galaxies. The force behind this imbalance remains unidentified. Another strange form of energy involves vacuum fluctuations. According to quantum theory, empty space is not truly empty. It contains pairs of particles that appear and disappear instantly. These fluctuations are incredibly small, but they exist everywhere. They affect atomic behaviour. They influence interactions in deep space, and they may be related to dark energy. Vacuum energy challenges our understanding of what nothing means. Even the emptiest region of space contains activity. Then there are cosmic magnetic fields. Magnetic fields exist throughout the universe. They thread through galaxies, clusters, and even intergalactic space, but their origin is unclear. Small magnetic fields can be amplified, but where did the first ones come from? Some galaxies contain magnetic fields so strong they influence gas motion on large scales. Some neutron stars contain magnetic fields trillions of times stronger than Earth's. These fields shape the behaviour of matter, but no one knows how they formed. Another strange force is radiation pressure in extreme environments. Near massive stars, radiation can push gas outward with tremendous force. This pressure can even stop star formation or blow apart entire clouds. In accretion, disks around black holes, radiation pressure helps shape jets and outflows. This force acts as a counterbalance to gravity, creating complex interactions. Now consider gravitational lensing. Gravity bends light, causing distant galaxies to appear distorted or multiplied. But some lensing effects are stronger than expected. This suggests concentrations of mass we cannot see. Some lensing patterns appear where there is no visible matter. These effects reveal dark matter's presence, but also show that gravity behaves differently in certain regions. Gravity is the most familiar force, yet it remains the least understood. It governs the motion of stars, planets, and galaxies. But integrating gravity with quantum mechanics remains one of science's biggest challenges. Another strange force appears in black holes. Near the event horizon, space-time becomes so curved that time slows dramatically. Light struggles to escape. Gravity becomes almost infinitely strong. But the most surprising force is something predicted by quantum theory: Hawking radiation. Black holes are not perfectly black. They slowly emit radiation due to quantum effects near the horizon. This radiation means black holes can evaporate over time. The existence of Hawking radiation suggests a deep connection between gravity, quantum physics, and thermodynamics. But it also creates one of the biggest mysteries: the information paradox. The information paradox arises because, according to quantum theory, information cannot be destroyed. Yet if a black hole evaporates completely, what happens to the information inside? Does it escape somehow? Does it remain encoded in the radiation? Or does something else happen at the event horizon? This question forces physicists to rethink the nature of information and energy. It hints at deeper laws that combine gravity and quantum mechanics. Another strange discovery involves cosmic acceleration. The expansion of the universe is not just increasing. The rate of acceleration appears inconsistent in different measurements. Some methods produce one value for the expansion rate. Other methods produce another. This Hubble tension suggests that something unexpected may be happening. Either dark energy is changing over time, or our understanding of cosmic expansion is incomplete. The disagreement may lead to a new model of the universe. Quantum entanglement adds another layer of strangeness. When two particles become entangled, their states remain linked regardless of distance. Changing one particle instantly changes the other. Entanglement appears to operate faster than light, though it does not transfer usable information. But entanglement also appears in black holes, where the information problem becomes more complicated. Some theories suggest space-time itself might be made of entanglement. If true, gravity and geometry may emerge from quantum relationships. Another strange form of energy appears in the early universe: inflation. Inflation is a rapid expansion that occurred just after the Big Bang. It stretched space-time faster than the speed of light. This expansion smoothed out the universe and explains why the cosmic microwave background is so uniform. But the force driving inflation remains unknown. It may be a field that vanished moments after the Big Bang, or it may have left behind signatures we have not yet detected. Cosmic rays also represent strange energy. Some cosmic rays strike Earth with energies far beyond anything produced in particle accelerators. The source of these ultra-high energy particles remains unclear. They may come from black hole jets, neutron star collisions, or exotic processes in the early universe. Their existence suggests that the universe contains accelerators far more powerful than anything we can build. These forces and energies reveal that the universe is not simple. It is full of hidden influences, subtle interactions, and unknown elements. Every strange force points toward deeper physics. Every anomaly tells us that our current models are incomplete. The universe runs on rules we only partially understand. These energies shape galaxies, stars, planets, and the large-scale structure of the universe. They determine how the cosmos evolves. They determine the universe's past and its future. They dictate how matter organizes itself and how space-time expands. In the next part, we explore the strangest relics from the early universe, signals, particles, structures, and leftovers from a time when the universe was young and chaotic. 11. The relics that survived the birth of the universe. Some of the strangest things we have discovered in space are not distant galaxies, unusual stars, or mysterious planets. They are relics, leftovers, frozen records from a time when the universe was very young, very hot, and very chaotic. These relics survived more than 13 billion years. They carry information from moments we can never witness. They reveal what the universe looked like long before galaxies formed. They show how matter behaved when physics operated under completely different conditions. These relics are not ordinary objects, they are fingerprints of creation. One of the most important relics is the cosmic microwave background. This faint glow fills all of space. It is the leftover heat from the Big Bang. When the universe was young, it was so hot and dense that atoms could not form. Light scattered constantly. But as the universe expanded and cooled, atoms formed and light finally travelled freely. That light stretched into microwaves over billions of years. Today, it appears as a faint signal surrounding us in every direction. But what makes it strange is not that it exists. What makes it strange are the tiny variations in temperature within it. These variations represent the earliest structures in the universe, or the seeds of galaxies, clusters, and cosmic filaments. They show that even in the earliest moments, the universe was not perfectly uniform. Something created tiny lumps of density that later grew into the structures we see today. Another relic is the abundance of light elements, like hydrogen, helium, and lithium. These elements formed within minutes after the Big Bang. No stars existed yet. No galaxies existed. These elements were created during a short period of intense nuclear reactions known as primordial nucleosynthesis. The exact ratios of these elements match predictions made from Big Bang theory. But there is a strange part. The amount of lithium in the universe does not match predictions. The discrepancy is known as the lithium problem. Something happened in the early universe that altered lithium production. We do not know what that process was. It may involve unknown particles or early universe physics that no longer operates today. Then there are relic neutrinos. The universe contains trillions of neutrinos from the early Big Bang. These relic neutrinos are extremely cold, extremely faint, and almost impossible to detect. Yet they fill the universe. They pass through everything. They preserve information about the universe seconds after it began. If we ever detect them directly, they will reveal details about the early expansion rate, early temperature, and the behavior of fundamental particles. But detecting relic neutrinos requires technology far beyond current capabilities. Another relic is dark matter itself. If dark matter particles formed in the early universe, they have existed unchanged for billions of years. Their distribution across the cosmic web reflects early conditions. The way dark matter clumps shows how density fluctuations grew over time. If dark matter is a relic of the Big Bang, then it carries information about physics and energies we cannot replicate. Some theories suggest dark matter formed through processes involving exotic particles that decayed early on. Others propose that dark matter came from an early phase transition in the universe. Whatever the truth, dark matter is a fossil of ancient physics. Now consider primordial black holes, hypothetical black holes that may have formed fractions of a second after the Big Bang. These black holes would not come from stars, but from extreme density fluctuations. Some could be microscopic, others could be massive. If primordial black holes exist, they could explain dark matter. They could have influenced galaxy formation. They could be scattered throughout the universe. But we have not confirmed their existence. Detecting them would reveal details about the earliest moments of the universe, when conditions were so extreme that normal physics breaks down. Another relic comes from gravitational waves. Some gravitational waves may come from the early universe itself, produced during cosmic inflation. These waves would carry information about the expansion of space-time when the universe was smaller than an atom. But detecting primordial gravitational waves is extremely difficult. Their signal would be faint and buried beneath other cosmic noise. If detected, they would provide direct evidence of inflation and reveal the physics that operated at unimaginable energies. The cosmic web is also a relic. Its large-scale structure, the filaments, voids, and clusters, reflects density differences in the early universe. These density differences grew under gravity. The patterns we see today mirror the tiny fluctuations in the cosmic microwave background. The universe's structure is a fossil of its earliest moments, but some features in the cosmic web are too large or too organized to fit simple inflation models. This suggests that early universe physics had more complexity than we assumed. Then there are the oldest stars. These stars formed when the universe was still young. Their compositions contain almost no heavy elements. They are made mostly of hydrogen and helium. These low metallicity stars reveal what the universe looked like before repeated generations of star formation created heavier elements. Some of these stars are more than 13 billion years old. They carry chemical signatures from the early universe, but some appear older than expected. Their ages challenge our understanding of star formation timelines. Another relic comes in the form of supermassive black holes that form surprisingly early. We have discovered black holes 1 billion times more massive than the Sun, forming only a few 100 million years after the Big Bang. Their existence is puzzling. How did they grow so quickly? Normal star formation and accretion cannot explain their rapid growth. This suggests that early universe conditions were far more efficient at forming massive black holes. These ancient giants are relics of an era when galaxies and black holes formed under extreme conditions. Then consider the oldest galaxies. Some early galaxies appear more massive, brighter, and more organized than expected. They challenge models of early galaxy formation. Their structure suggests that matter clumped together faster than predicted. These galaxies carry information from the first billion years of the universe. Their unusual properties act as clues about early cosmic conditions, yet they remain difficult to explain with current theories. Another relic comes from the distribution of galaxy clusters. Some clusters are too massive for their age. They formed earlier than models predict. These enormous clusters require large amounts of dark matter and rapid early collapse. Their existence suggests that early gravitational structures formed faster or differently than expected. Now consider cosmic background radiation beyond microwaves. There may be backgrounds of neutrinos, gravitational waves, and other unknown particles left from the early universe. Some may never be detectable. But if even one of these backgrounds is found, it will reveal new physics. The early universe was filled with processes we cannot reproduce. These relics offer the only window into that era. Then there is baryogenesis, the process that created matter. We know matter dominates the universe, but we do not know why. Something in the early universe created an imbalance between matter and antimatter. This imbalance is the reason anything exists at all. Whatever caused baryogenesis left relics in particle distributions and cosmic structure. Another strange relic is the possible existence of domain walls or cosmic strings, hypothetical structures formed during early universe phase transitions. These structures would be thin, extremely dense lines or surfaces stretching across the universe. If they exist, they could influence galaxy formation or gravitational wave backgrounds, but no direct evidence exists yet. Cosmic strings and domain walls remain theoretical relics, but they represent the possibility that the early universe left behind structures we have not yet detected. Even quantum fluctuations in the early universe are relics. These tiny fluctuations, magnified by inflation, seeded all cosmic structure. Their distribution tells us about early universe physics. Some fluctuations appear slightly stronger or weaker than expected. These differences may point toward unknown fields or forces active during inflation. These relics all share one theme. They reveal the universe not as it is now, but as it once was. They freeze moments of cosmic history into patterns and structures we can study. Every relic is a message from the past. Every irregularity is a clue. Every unexpected feature tells us something about the early conditions that shaped everything. The universe keeps its history hidden in light, particles, structures, and patterns. Reading that history requires looking deeper, detecting fainter signals, and reconsidering assumptions. The early universe was a place of rapid change, extreme conditions, and unfamiliar physics. Relics are the only evidence we have of that era. They show that the universe has been strange from the very beginning. In the next part, we explore the strangest voids and empty regions of space where nothing exists, yet the emptiness itself behaves in mysterious ways. 12. The voids where nothing should exist, yet something feels wrong. Space is mostly empty, but some regions are so empty that they should not exist at all. These are cosmic voids, vast spaces containing almost no galaxies, no clusters, and sometimes no visible matter at all. They stretch across hundreds of millions of light years. They appear as giant holes in the cosmic web. But what makes them strange is not just their emptiness, it is their size, their shape, and the way they influence the movement of galaxies around them. Some voids are too large, some are too cold, some appear to be growing in unusual ways, and some contain strange anomalies that do not fit into any standard model of cosmic structure. A normal void contains fewer galaxies than average, but it still contains some matter. Gravity pulls galaxies into filaments, leaving gaps between them. These gaps form naturally, but certain voids we have discovered are so extreme that they challenge everything we know about how matter spreads in the universe. One of the strangest examples is the Eridanus supervoid, often called the cold spot void. This region is unusually cold in the cosmic microwave background. The temperature difference is small but significant. When astronomers investigated, they found a massive void hundreds of millions of light years wide. Theories suggest that light travelling through the void loses energy differently because the void lacks mass. But the size of the void is too large to be explained by standard cosmic evolution models. Its existence remains one of the biggest puzzles in cosmology. Another strange void is the Bootes void. It is one of the largest known voids, roughly 330 million light-years across. If the universe were random, such a void should almost never form. Yet there it is, an enormous spherical region with very few galaxies. Only a handful of galaxies are found inside, and they are scattered far apart. The Bootes void appears almost artificial in its emptiness. Its formation may have involved multiple smaller voids merging, or it may indicate that early density fluctuations were far more dramatic than predicted. The void's near-perfect roundness also raises questions about large-scale cosmic structure. Some voids show unexpected shapes and boundaries. Instead of being random, they align with surrounding filaments in surprising ways. This suggests that voids may grow directionally, influenced by forces beyond simple gravity. Dark energy may play a role in how voids expand. Some voids appear to push surrounding matter away, contributing to local galaxy flows. This would make voids active participants in cosmic motion, not passive gaps. Another puzzling phenomenon is the behavior of galaxies near voids. Galaxies at the edges of voids move in unusually coherent patterns. They appear to flow along the boundaries, as if sliding down the walls of the cosmic web. In some cases, galaxies move faster than expected relative to the void. This motion may indicate that voids expand more rapidly than previously believed. If voids expand faster, it could mean that dark energy behaves differently in low-density regions. This would have major implications for cosmology. Some voids contain faint, isolated galaxies that themselves behave strangely. These galaxies often have unusual shapes, low metallicity, and unexpected star formation histories. They exist in environments with almost no nearby gravitational influence. Without outside pressure, their evolution becomes unusual. Some void galaxies show irregular structures that appear stretched or disrupted without clear cause. Others form stars at unusually slow rates. The extreme isolation inside voids creates conditions very different from the crowded environments of galaxy clusters. Then there are mini-voids, smaller, local regions of emptiness within the cosmic web. These mini-voids might seem less dramatic, but they play a major role in shaping galaxy distribution. Some mini-voids appear in places where models predict galaxy groups. Their absence suggests that small-scale structure formation may not behave as predicted. The existence of too many or too few mini-voids is one of the major challenges in matching observations with simulations. Another strange feature of voids is their potential interaction with dark matter. Dark matter should influence how voids form and evolve. But mapping dark matter in void regions is difficult because there is little visible matter to trace gravitational effects. Some voids appear to lack dark matter entirely. Others show dark matter concentrations where we expect none. This inconsistency suggests that dark matter may behave differently in low-density environments, or that our detection methods are incomplete. The shape of voids also raises questions. Some voids are elongated, others are flattened. Some form chains or clusters of emptiness. These shapes suggest that the cosmic web evolves through processes we do not fully understand. Interactions between dark matter, dark energy, and normal matter may play a role, but simulations struggle to reproduce the exact features of observed voids. Another strange aspect is that voids appear to influence cosmic expansion. Some studies suggest that voids expand faster than the universe as a whole. This accelerated expansion could amplify differences in galaxy distributions. If true, voids may help explain the Hubble tension, the disagreement between different measurements of the universe's expansion rate. The idea is that our location in the cosmic web affects how we measure expansion. If we live near a void or on the edge of one, it could skew observations. Then there is the concept of supervoids. Supervoids are massive regions that combine multiple voids into a single structure. They can span more than 1 billion light-years. These supervoids are so large that they should not form under simple gravitational collapse models. Their existence suggests that early universe fluctuations were more extreme than predicted, or that cosmic inflation created larger density differences than expected. The idea of void walls is also intriguing. Voids often have sharp boundaries where galaxy density suddenly increases. These boundaries look like cosmic walls. They are part of the cosmic web, but their sharpness suggests that matter flowed into them in organized ways. The formation of these walls remains a subject of study. They may reveal how dark matter shaped the early universe. Another strange concept is the void-in-cloud effect. Sometimes voids form inside regions with overall high density. These voids collapse or distort as surrounding matter pulls inward. Their behavior is unpredictable. Some voids shrink, others flip shape. Their evolution depends on the balance between local density and larger-scale gravitational forces. These effects show how complex and dynamic void environments can be. Voids also contain extremely low temperatures. Because they lack stars, galaxies, and gas clouds, their temperatures drop far below the cosmic average. Some regions inside voids reach temperatures that appear too cold, even after accounting for the absence of matter. These anomalies may reflect unusual interactions with dark energy or differences in cosmic radiation density. Another strange aspect of voids is the lack of heavy elements. Galaxies in voids often show chemical compositions similar to early universe galaxies. This suggests limited star formation over billions of years. Without interactions, mergers, or inflows of enriched gas, these galaxies remain chemically primitive. This preservation of early conditions makes them valuable relics. Yet their isolation raises questions about how they formed in the first place. Then there is the mystery of void. Alignment. Some voids appear to have similar orientations or shapes over large distances. This large-scale alignment hints at early universe influences that operate beyond simple gravitational collapse. These alignments challenge the assumption that the universe is isotropic, the same in all directions. Voids also contain gravitational potential differences. Light passing through voids loses energy differently compared to denser regions. This creates subtle distortions in cosmic microwave background maps. These distortions can indicate the presence, size, and shape of voids, but in some cases the distortions are larger or smaller than expected. This inconsistency suggests that void physics may require new theories. Another mystery involves the possible connection between voids and cosmic acceleration. Some theories propose that voids contribute to the measured acceleration of the universe. They suggest that the expansion of voids creates an illusion of accelerated expansion. While this idea does not replace dark energy, it highlights how structure influences cosmological measurements. Voids show us that emptiness is not simple. Emptiness behaves, emptiness evolves, emptiness can influence motion, temperature, and cosmic history. Voids are as important as galaxies in shaping the universe. Their size and behavior reveal how matter and energy spread across cosmic scales. These giant empty spaces force us to rethink what nothing means in the universe. Nothingness can have structure. Nothingness can create effects. Nothingness can be one of the strangest discoveries of all. In the next part, we explore the oddest behaviors of space-time itself, including bending, stretching, twisting, and phenomena that suggest space-time might not be as smooth and simple as it appears. 13. The space-time behaviors that make reality feel unreal. Space is not just a stage where objects move. Space is active. Space bends. Space stretches. Space flows. Space reacts to mass, energy, and motion in ways that feel impossible from a human point of view. When Einstein described space-time as a fabric, it sounded poetic, but the truth is stranger. Space-time has behaviors. It has tension, it has curvature, it can ripple, it can twist, it can drag matter along with it. And some of these behaviors do not match our intuition at all. They show that reality itself is not built the way we assume. One of the strangest behaviors of space-time is gravitational lensing. Light should travel in straight lines, yet light bends around massive objects. This bending is not caused by a force pulling on the light. It happens because space-time itself curves. When space-time curves, the shortest path between 2 points is no longer a straight line. Light follows that curved path. In extreme cases, this bending can duplicate images of galaxies, stretch them into arcs, or magnify them like lenses. Some of the brightest distant galaxies we observe are only visible because giant clusters act as magnifying glasses. But gravitational lensing becomes stranger when it occurs where almost no visible mass exists. These dark lenses reveal concentrations of dark matter shaping space-time without emitting any light. Another strange behavior is gravitational time dilation. Time passes differently depending on gravity. Clocks near massive objects run slower than clocks farther away. This is not a theoretical idea. It is measured every day. GPS satellites adjust their clocks because time moves slightly faster in orbit than on Earth's surface, but the difference becomes extreme near black holes. A person near a strong gravitational field ages slower than someone far away. This means space-time does not treat time equally. Time itself stretches and compresses depending on gravity. Then there is frame dragging, the twisting of space-time by rotating objects. When a massive object spins, it drags space-time around with it, like a spoon stirring water. This effect has been measured around Earth, but it becomes powerful near neutron stars and black holes. In these environments, space-time swirls at incredible speeds. This twisting can change orbital paths, shift jets of plasma, and distort magnetic fields. Frame dragging shows that space behaves like a fluid when pushed by rotation. Another strange behaviour is the warping of space-time caused by motion. According to relativity, motion affects both time and space. As an object moves faster, time slows for it relative to observers at rest. lengths contract along the direction of motion. This effect is tiny at everyday speeds but becomes significant near the speed of light. It means space-time reacts to motion, not just by stretching time, but by altering physical dimensions. Space is not fixed, it responds to how fast things move. Then there are gravitational waves, ripples in space-time created by massive collisions. When black holes merge, space-time vibrates. These vibrations spread outward across the universe. By the time they reach Earth, they are incredibly weak, but sensitive detectors can measure them. Gravitational waves were first detected in 2015, confirming a prediction made a century earlier. These waves show that space-time can oscillate like water. They also reveal events that light cannot show: black hole mergers, neutron star collisions, and other extreme processes. Gravitational waves allow us to hear the universe in a new way. Another strange behaviour is that space-time appears smooth, but may not be truly continuous. At quantum scales, space-time might look grainy or jittery. Quantum fluctuations may cause tiny distortions. These fluctuations might influence particle behaviour or early universe inflation, but we cannot observe them directly. If space-time is not perfectly smooth, then our understanding of gravity may need to change. Quantum gravity theories attempt to describe space-time at the smallest scales, but none have been confirmed. Now consider the expansion of space-time. The universe is not just full of galaxies moving through space. Space itself expands. This expansion stretches the distance between galaxies. As expansion accelerates due to dark energy, galaxies move away faster. Some move away faster than light, not because they exceed the speed limit, but because space stretches between us and them. This expansion changes the structure of the universe. It also influences how we measure distances. Expansion is one of the strangest behaviours of space-time because it involves stretching that affects everything. Even light gets stretched into longer wavelengths as space expands. Another strange behaviour involves the possibility of space-time curvature without mass. Some theoretical models propose that space-time can curve due to energy fields that do not resemble matter. These fields could create pockets of curvature that influence motion. They could explain certain anomalies in galaxy rotation or cosmic acceleration. But such curvature without mass has not been directly observed. Still, the possibility reveals how flexible space-time may be. Then there are wormholes, theoretical tunnels connecting distant parts of space-time. Wormholes appear in solutions to Einstein's equations, but we do not know if they exist in the real universe. If they did, they would allow shortcuts through space-time, but they would require exotic matter to remain stable. Exotic matter would have negative energy density, something not observed in everyday physics. Wormholes remain mathematical curiosities, but they show that the equations describing space-time allow for possibilities far beyond our experience. Another strange behaviour is the violation of global simultaneity. There is no universal now in the universe. Two observers moving differently may disagree on the sequence of events. Something that appears simultaneous to one observer may appear sequential to another. This relativity of time makes it impossible to describe the universe in a single, shared timeline. Space-time does not offer a universal clock. It offers only local time frames shaped by motion and gravity. Then, there is the bending of space-time by pressure and energy. Most people think only mass bends space-time, but pressure, heat, and energy also curve space. Even light contributes to curvature, despite having no mass. This means that radiation-filled regions of the universe can warp space differently from cold regions. High-energy environments, near stars and black holes, curve space-time more intensely. This reveals that gravity is not just caused by mass, but by all forms of energy. Another strange behaviour is that space-time might allow negative energy under certain quantum conditions. Negative energy could create repulsive gravitational effects. It might stabilise wormholes or warp bubbles. It might influence cosmic expansion. Negative energy is theoretical, but experiments involving quantum fields show tiny hints of such behaviour. If negative energy plays a role in the cosmos, it could rewrite our understanding of gravitational balance. Space-time also allows something called cosmic censorship, the idea that singularities cannot be visible. In most realistic solutions, singularities remain hidden behind event horizons. But no one knows if this rule always holds. A naked singularity, a singularity visible without a horizon, would break many assumptions about causality and physics. Space-time might allow such objects under certain conditions, although none have been observed. Another strange feature is the possibility of closed time-like curves. These are loops in space-time that allow an object to return to its own past. Solutions to Einstein's equations allow these curves under certain conditions, such as near-rotating black holes. But whether they are physically possible is unknown. They challenge causality. They show that space-time does not completely forbid paths that loop in time. Then there is the behaviour of space-time near a singularity. As matter collapses inward, curvature becomes infinite. Time and space switch roles. The laws of physics break down. We cannot describe what happens inside a black hole because space-time becomes undefined. This unknown region is one of the strangest ideas in physics, a place where the rules fail. Another strange behaviour is the possibility that space-time might be emergent. Instead of being fundamental, space-time might arise from quantum entanglement. In this view, geometry is not the foundation, but a side effect. Space exists because information is connected. Gravity exists because entanglement creates curvature. This emerging idea suggests that space-time might be built from something deeper, something not yet measured directly. Space-time does not behave like a rigid grid. It behaves like a living structure that changes with mass, energy, motion, and quantum effects. It bends when matter gathers. It stretches when energy spreads. It ripples when massive objects collide. It slows time. It twists space. It expands everywhere at once. And at its edges near singularities in quantum fluctuations or in early universe conditions, it becomes almost unrecognizable. The strangest discoveries in space are not always objects floating in darkness. Sometimes the strangest discoveries are the rules that govern the darkness itself. In the next part, we explore the strangest interactions in the universe, collisions, mergers, disruptions, and transformations where cosmic forces combine to create phenomena that defy expectations. 14. The interactions that turn space into something unrecognizable. Space is full of collisions, mergers, disruptions, and violent encounters. These interactions reshape matter, twist gravity, and transform entire regions of the universe. When stars collide, when galaxies merge, when black holes interact, the results are unlike anything we experience in everyday life. The universe is not static. It is constantly rearranging itself through encounters that push physical laws to their limits. Some of these interactions are predictable. Others behave in strange and unexpected ways that reveal gaps in our understanding. These cosmic events show how dynamic and unpredictable space truly is. One of the strangest interactions happens when two neutron stars merge. Neutron stars are already some of the densest objects in the universe. When they spiral inward and collide, the energy released is enormous. The collision produces gravitational waves strong enough to ripple space-time across billions of light years. It also creates heavy elements like gold, platinum, and uranium. But what makes neutron star mergers truly strange is the moment after the collision. Sometimes a black hole forms. Sometimes a supermassive neutron star forms temporarily before collapsing. Sometimes the remnant survives longer than expected. Each outcome reveals different internal structures and physical processes. These mergers act as laboratories for extreme physics, showing us how matter behaves under pressures we cannot replicate. Then there are black hole mergers. When two black holes spiral into each other, their interaction is pure gravity. No light escapes, no matter is exchanged. The only signal is a burst of gravitational waves. But some black hole mergers produce spins and final masses that seem unusual. A few mergers have created black holes heavier than predicted by stellar evolution models. Others show odd tilts or unexpected spins. These strange results suggest that black holes may have merged multiple times in dense clusters, or that their formation involved processes we do not fully understand. Some merger signals even hinted at possible intermediate mass black holes, which are rare and difficult to confirm. Another strange interaction occurs when black holes interact with stars. Sometimes a star wanders too close and gets torn apart. The star stretches into a long stream of gas, spiraling toward the black hole. This process creates a tidal disruption event. These events produce intense flares of radiation and chaotic motion in the gas. But some tidal disruption events behave in puzzling ways. Some flare for longer than expected. Some show unusual brightness patterns. Some produce jets that shoot outward at near-light speed. These irregularities suggest that black hole feeding is more complex than simple accretion. The magnetic fields, the star's composition, and the black hole's spin all play roles in ways we do not fully understand. Interactions between stars can also be strange. Binary stars exchange material. Some stars steal gas from their companions, creating accretion disks. Others merge to form larger stars. Some binaries evolve into exotic objects like blue stragglers, which appear younger than the surrounding stars. These youthful-looking stars puzzled astronomers for decades until they were understood as merger products. But some blue stragglers appear in environments where mergers should be rare. Their existence suggests that certain interactions happen under conditions we do not fully understand. Another strange type of interaction occurs when white dwarfs collide. These collisions can create unusual supernovae. Some supernovae are too faint. Others are too bright. Some show chemical signatures that do not match expected models. These peculiar supernovae reveal that not all stellar explosions follow the same pathways. Interactions between compact stars may produce outcomes that differ from traditional models. Galaxies also interact in unexpected ways. When galaxies collide, their shapes distort. Stars form new patterns. Gas clouds compress, triggering bursts of star formation. But some interactions form unusually long, tidal tails, or ring-like structures. Some create empty-looking gaps. Others produce galaxies with double cores. These complex shapes arise from gravitational interactions, yet some patterns appear too organized or too symmetric to be simple collision debris. These collisions often produce elliptical galaxies, but some produce shapes that look almost sculpted. The details depend on the angles of collision, relative speeds, and gas content, making each merger unique. Then there are flyby interactions, when galaxies pass close to each other without merging. These encounters cause gravitational tides that can stretch spiral arms, distort disks, or fling stars into intergalactic space. Some galaxies have long streams of stars trailing behind them from past flybys. These stellar streams reveal the history of interactions millions or billions of years old. But some streams do not match expected patterns, suggesting either unusual orbits or interactions with unseen masses. Another strange interaction involves galaxy clusters. Cluster collisions produce enormous shock waves and vast clouds of heated gas. The Bullet cluster is a prime example. When two clusters collided, the dark matter passed through with little interaction, while the hot gas lagged behind. This separation between dark matter and normal matter confirmed that dark matter behaves differently during interactions. But some clusters show partial separation or unexpected shapes, suggesting complexity in how dark matter moves. These observations raise questions about the nature of dark matter itself. Interactions between galaxies and their environments can also be strange. Some galaxies lose gas as they fall through clusters due to ram pressure stripping. The galaxy plows through hot gas, and the gas inside the galaxy gets pushed out. This process creates long tails of material. In some cases, these tails form new stars. In others, they form ghostly trails of ionized gas. The varying behavior suggests that interactions depend heavily on cluster conditions, galaxy speed, and internal structure. Then there are gravitational interactions with dark matter halos. Every galaxy sits inside a halo of dark matter. When galaxies interact, their halos interact too. But these halos do not behave like normal matter. They pass through each other without friction, yet they still influence motions. Some galaxies show warped disks or unusual rotation curves due to halo interactions. These distortions hint at the shapes of dark matter halos, which may be elongated or clumpy. Understanding these interactions helps us map invisible structures. Another strange interaction involves jets from black holes. These jets shoot outward at nearly the speed of light. They interact with surrounding gas, drilling cavities in galaxy clusters. These cavities, known as radio bubbles, can grow to enormous sizes. The energy required to create them is immense, but the exact mechanism that produces jets remains unclear. Magnetic fields and spinning black holes play roles, but the details are still debated. The interaction between jets and their environments shapes galaxy evolution in ways we do not fully understand. Some interactions occur on even larger scales. Cosmic filaments interact with galaxy clusters as matter flows inward. This flow shapes cluster growth, but the flow often forms patterns too smooth or too coherent to be random. Filament interactions seem to follow deeper cosmic rules, suggesting large-scale behavior influenced by dark matter distribution. Another strange phenomenon involves star formation, triggered by collisions. When two galaxies merge, star formation often increases dramatically, but sometimes mergers suppress star formation instead. This irregular behavior depends on gas dynamics, feedback processes, and black hole activity. Understanding this interaction is crucial for explaining galaxy evolution. Then there are interactions involving planets. Some planetary systems contain planets in unstable orbits due to past gravitational interactions. Some planets were likely ejected from their systems and now drift through space as rogue planets. These planets form through interactions that disrupt orbits, especially in young star clusters. The existence of rogue planets shows that planetary systems are dynamic and chaotic. Another strange interaction occurs when massive stars blow powerful winds that interact with nearby gas clouds. These winds carve cavities, compress regions, and shape nebulae. But some nebulae have shapes that are difficult to explain with simple wind models. The interaction between radiation pressure, magnetic fields, and gas dynamics creates patterns that look almost artistic. Then there are interactions between cosmic rays and interstellar gas. Cosmic rays can ionize gas, trigger chemical reactions, and influence star formation. Their energy comes from supernova, black hole jets, and other extreme events. But their exact effects remain poorly understood because cosmic rays interact with magnetic fields in complex ways. Another strange category involves the interactions that occur near black hole accretion disks. Gas spirals inward, heats up, and emits radiation. But the detailed behavior of accretion disks remains mysterious. Some disks flicker unpredictably. Some show consistent quasi-periodic oscillations. Some produce sudden flares. These variations reveal turbulence, magnetic reconnection, and other complex processes happening near the event horizon. Interactions at the quantum level also occur in space. Particles from the solar wind interact with Earth's magnetic field, creating auroras. But similar interactions happen on much larger scales near other stars and planets. These processes show how magnetic fields mediate energy transfer across space. Every strange interaction in the universe shows that space is not empty. It is active. Forces push, pull, twist, and collide. Matter responds in ways that are sometimes expected and sometimes completely surprising. These interactions shape galaxies, stars, planets, and cosmic structures. They create new objects. They destroy old ones. They leave behind relics that last for billions of years. The universe is not static. It is dynamic, alive with movement and transformation. Interactions reveal the universe's inner workings. They expose the balance of forces that govern everything. In the final part, we explore the strangest possibilities for the future of the universe, how it might evolve, how it might end, and what these discoveries suggest about the ultimate fate of space and time. 15. The future. That space is slowly revealing. The universe is full of strange discoveries, but perhaps the strangest thing of all is what these discoveries imply about the future. Space is not finished changing. Stars will die, galaxies will evolve, structures will drift apart, black holes will grow, merge, and eventually fade. Dark energy will continue shaping the fate of the cosmos. Every strange object, every unexplained force, every unusual motion is part of a much larger story, a story about where the universe is heading. The future of space is far more dramatic, far more mysterious, and far stranger than anything we see today. One of the most important clues about the universe's future comes from dark energy. Dark energy is pushing galaxies away from each other, faster and faster. If this trend continues, galaxies that are already distant will eventually move so far away that their light will never reach us. The observable universe will shrink, not physically, but visually. Future civilizations may see only their own galaxy. Everything else will fade beyond the cosmic horizon. This isolation would make the universe feel smaller, even while it expands. Understanding dark energy is essential because it determines whether the expansion continues forever or changes over time. If dark energy remains constant, the universe will continue expanding at an accelerated rate. Galaxies will grow farther apart. Stars within galaxies will continue their life cycles. New stars will form, but gradually fewer over time. Eventually, star formation will slow as gas becomes harder to gather. The universe will enter a stage known as the degenerate era, when most stars have already formed, aged and died. The bright, active universe we see today is a temporary phase. The future will be darker, emptier and quieter. But dark energy might not remain constant. It could grow stronger. If it increases over time, the expansion will accelerate even more. In extreme scenarios, dark energy could tear apart galaxies, solar systems, stars, and eventually even atoms. This hypothetical scenario is known as the Big Rip. In this ending, space-time itself would stretch faster than anything can hold together. Structures would dissolve, energy fields would unravel, even the fabric of the universe could be torn apart. This scenario is speculative, but it shows how much influence dark energy could have. Another possibility involves the far future of black holes. Black holes dominate the long-term evolution of the universe. Over trillions of years, stars will die, leaving behind white dwarfs, neutron stars, and black holes. Most matter will end up inside black holes or drifting alone in the cold void. Black holes themselves will merge over time, creating larger and larger black holes. Eventually, only supermassive black holes will remain, giants at the centres of dead galaxies, but even black holes are not eternal. They emit Hawking radiation. Over unimaginable timescales, they slowly evaporate. Small black holes evaporate quickly. Large ones take longer. Supermassive black holes could last for tens of trillions of years or more. When they finally evaporate, the universe will enter a stage where no large gravitational structures remain. The evaporation of black holes marks the beginning of the universe's descent into darkness. After the black holes vanish, the universe will contain only faint radiation and leftover subatomic particles. These particles will drift through an almost infinite void. Temperatures will approach absolute zero. This scenario is known as the heat death of the universe. In heat death, energy becomes so evenly spread that no more work can be done. No stars shine, no galaxies rotate, no interactions occur. The universe reaches a state of maximum entropy where nothing changes. But the future may not be that simple. Some theories suggest the universe could experience a bounce, a contraction after expansion. If dark energy changes sign, the universe could slow down, stop expanding, and begin collapsing. This collapse would reverse the cosmic flow. Galaxies would move closer. Temperatures would rise, structures would compress. Eventually, everything would collapse into a hot, dense state, similar to the conditions before the Big Bang. This scenario is known as the Big Crunch. It could potentially lead to a new expansion, creating a cycle of universes. But evidence currently favours continued expansion, not collapse. Another strange possibility involves quantum fluctuations. Even in a near-empty universe, quantum fields remain active. Over long periods, random fluctuations could create new regions of space-time. These regions might inflate into new universes. Our universe might be one bubble in a larger multiverse. If so, the end of our universe might simply be one phase in an infinite cosmic landscape. New universes could appear even as others fade. The behaviour of dark matter also shapes the future. If dark matter particles decay over time, the structure of galaxies could slowly dissolve. Gravity would weaken. Stars would drift apart. The timeline of cosmic evolution would change. But if dark matter is stable, galaxies will persist much longer. Understanding the fate of dark matter is essential for predicting cosmic structure billions of years into the future. Another clue about the future comes from stellar evolution. Stars like the Sun will eventually become red giants, then white dwarfs, and then cool into black dwarfs. More massive stars will explode as supernovae, leaving behind neutron stars and black holes. The population of stars will shift toward compact, faint objects. The bright era of starlight will end. But before it ends completely, unusual long-term processes will occur. Some stars may collide due to slow orbital changes. Others may absorb planets or be disrupted by passing stars. Over trillions of years, even these interactions will fade. Planets also have strange futures. Orbits change slowly, over millions and billions of years. Some planets will drift closer to their stars. Others will drift outward. Some will be ejected from their systems entirely. Rogue planets will drift through space indefinitely. Over long timescales, planetary systems become unstable. Even stable systems can become chaotic due to gravitational interactions. These changes create a future universe full of lonely planets and dead stars drifting in silence. Another strange future possibility comes from proton decay. If protons decay over extremely long timescales, then matter itself is not stable. Galaxies, stars, planets, and all normal matter would eventually dissolve into radiation. This idea is theoretical, but if true, it means the universe will eventually lose all structure. Proton decay would accelerate the universe's path toward heat death. But if protons are stable, matter could persist far longer. Some theories propose the existence of vacuum decay, a sudden transformation of space-time into a lower energy state. If such a transition occurred, it would spread at the speed of light, rewriting the laws of physics instantly. The universe would change fundamentally, leaving no time for anything to react. This hypothetical event is extremely unlikely on human timescales, but it is one of the strangest possibilities for the universe's distant future. Another possibility involves dark energy changing its behavior. If dark energy weakens, the universe could transition to a slower expansion. If dark energy oscillates, the universe could experience cycles of rapid and slow expansion. These cycles might influence the formation of future structures. Some models even suggest that dark energy could reverse, causing contraction. The future of cosmology depends heavily on the nature of this mysterious force. Even gravitational waves will play a role in the far future. As galaxies merge, black holes collide, and stars interact, gravitational waves will continue carrying energy away. Over long timescales, these waves will smooth out irregularities. They will help dissipate energy, pushing the universe toward equilibrium. In the far future, only the strangest objects will remain active. Quantum fluctuations, faint particles, evaporating black holes, subtle interactions between long-lived particles. The universe will evolve into a place where almost nothing happens, yet physics still operates quietly in the background. But perhaps the most mysterious question is whether the universe has a purpose or direction. Everything we observe suggests that the universe changes because of physical laws, not goals. Yet the structure, complexity, and scale of the universe create patterns that feel almost intentional. Life arose in one corner of a vast cosmos. Intelligence emerged and now tries to understand the universe's meaning. Our curiosity is part of the universe's story. Every strange discovery adds to our understanding. Every unanswered question pushes us deeper into the unknown. The future of the universe depends on factors we have only begun to understand. Dark energy, dark matter, quantum gravity, space-time behavior. These forces shape everything, yet we do not fully grasp them. The universe could fade quietly, it could collapse violently, it could transition into something new. It could spawn new universes, or it could behave in ways that no theory has predicted. The strangest discoveries in space are not just objects or phenomena. The strangest discoveries are the clues pointing to a universe that is far more complex and far more mysterious than our current understanding allows. We are living in a moment when we can observe galaxies billions of light years away, detect gravitational waves, measure cosmic backgrounds, and discover new particles. But even with all this knowledge, the universe remains full of surprises. The future will bring new mysteries, new discoveries, new theories. The more we learn, the stranger the universe becomes. And that is what makes exploring it so remarkable. Every discovery, no matter how strange, brings us closer to understanding the place we live in. A universe that is vast, powerful, unpredictable, and endlessly fascinating. The universe is far stranger than anything we could have imagined. Every discovery opens another door. Every answer reveals a deeper question. We look at distant stars, ancient relics, violent collisions, mysterious signals, and forces we barely understand, and we realize how small we are, yet how connected we are to all of it. The strangest things in space are not just objects floating in the dark. They are reminders that the universe is still growing, still changing, and still surprising us. And the more we explore, the more we see that the cosmos is not just a place. It is a story we are only beginning to read. Thank you for watching. If you enjoyed this journey through the unknown, make sure to like, share, and subscribe. There is so much more to discover out there, and we're just getting started.